What if I told you that every space mission you've ever watched, every Mars colony plan, every science fiction dream of humanity spreading across the cosmos is built on a foundation that's about to crumble beneath our feet? Right now, as you're watching this, there are astronauts on the International Space Station experiencing something so fundamentally disturbing about leaving Earth that NASA has kept most of the details classified for decades. Their bones are dissolving at a rate that would make them wheelchair-bound after just 2 years in space. Their eyeballs are literally changing shape, causing permanent vision damage that we still don't understand. And here's the really terrifying part. These are the problems we know about, the ones we can see, the ones happening just 250 miles above Earth's surface. Imagine what happens when we try to go millions of miles away. I'm going to show you why the universe itself seems designed to keep us exactly where we are. Why the very laws of physics appear to have conspired to make Earth not just our home, but our prison. And by the end of this video, you'll understand why the greatest minds in science are starting to whisper something that sounds like heresy. Maybe we were never meant to leave. But before we dive into this rabbit hole together, do me a favor. Hit that like button right now, because you're about to have your entire understanding of humanity's future completely transformed. Subscribe and turn on notifications, because this is just the beginning of understanding our cosmic predicament. And drop a comment telling me where you're watching from and what time it is in your location. I want to know how many people around the world are discovering this truth at the exact same moment. Are you in Tokyo at 3 a.m.? London at dinner time? New York during your lunch break? Let me know, because this global conversation is about to get very real. Now, let's talk about why we're trapped. You think space is empty, don't you? Just a vast vacuum where nothing exists. That's what they taught us in school. That's what every space movie shows us. Stars, planets, and nothing in between. But here's what will blow your mind. Space isn't empty at all. And the things filling it are actively trying to kill you in ways so creative, so relentless, that it makes Earth's harshest environments look like a tropical vacation. Let me introduce you to something called cosmic radiation, but not the sanitized version you learned about. I'm talking about the real, visceral nightmare that every astronaut faces the moment they leave Earth's protective embrace. Think of it like this. Imagine standing in a shooting range where billions of invisible bullets are flying at you from every direction, every second, moving at nearly the speed of light. Some of these bullets are so small, they pass right through your body. Others hit your DNA directly, snapping the delicate molecular chains that make you who you are. Now imagine you can never leave that shooting range. That's space. In 1972, astronaut Harrison Schmitt was on the moon during Apollo 17. He described seeing light flashes even when his eyes were closed. For years, scientists dismissed this as an optical illusion. They were wrong. Those flashes were cosmic rays passing directly through his eyeballs, hitting his retinas, creating actual light signals in his brain. He was literally seeing radiation as it destroyed parts of his cells. And here's the kicker. He was only there for 3 days. The moon, at least, offered some protection when he was on the surface. In deep space, there is no surface to hide behind. Dr. Francis Cucinoda, NASA's chief radiation health officer, published a study in 2013 that should have ended all talk of Mars missions. His team calculated that during a round trip to Mars, which would take about 2.5 years with current technology, astronauts would receive radiation doses equivalent to getting a full-body CT scan every 5 or 6 days. For 2.5 years, non-stop, the cancer risk jumps to nearly 5% per person. That might not sound like much until you realize that NASA's current acceptable risk threshold is 3% for an entire career. A single Mars mission would nearly double that. But cancer is the slow death. Let me tell you about the fast one. In 1859, something happened that changed our understanding of the sun forever. A British astronomer named Richard Carrington was observing sunspots through his telescope when he witnessed a massive explosion on the sun's surface. Within hours, a wave of charged particles slammed into Earth's magnetic field with such force that telegraph wires burst into flames. Operators received electric shocks. The aurora borealis appeared as far south as the Caribbean. This event, now called the Carrington event, was a coronal mass ejection, and it's exactly the kind of thing that could hit astronauts in space with zero warning. Here's what would happen. If a CME of that magnitude hit a spacecraft in deep space, the radiation dose would be instantly lethal. Not you'll get cancer in 20 years lethal. Not even you'll die in a few days lethal. We're talking about acute radiation syndrome developing within hours. Your immune system collapses. Your intestinal lining dissolves. You bleed internally. And you're millions of miles from help, floating in a tin can, watching your crewmates die the same way. Think of it like being a fish who wants to explore the land. Sure, you can flop around on the beach for a few minutes, maybe even a few hours if someone keeps splashing water on you. But you're not adapted for it. Every second away from water is killing you. Earth's magnetic field is our water. The Van Allen radiation belts, those zones of trapped particles surrounding our planet, are our gills. Without them, we suffocate under an invisible barrage of destruction. And it gets worse. In 2016, Dr. Michael Delp from Florida State University published research that made headlines for about a day before being quietly buried in the news cycle. He studied every astronaut who had been to deep space beyond Earth's magnetic field during the Apollo missions. His finding? They were dying from cardiovascular disease at a rate 4 to 5 times higher than astronauts who stayed in low Earth orbit. 4 to 5 times. Something about leaving Earth's protection fundamentally breaks human cardiovascular systems in ways we still don't understand. The radiation isn't just causing cancer. It's destroying the very vessels that keep blood flowing through our bodies. We've sent 12 humans beyond low Earth orbit. 12. And they were only there for a few days each. Already, we're seeing a pattern of early death from heart attacks and strokes. This isn't speculation. This isn't theory. This is hard medical data from the only humans who have ever ventured beyond our planet's magnetic shield. And the data is screaming at us. Don't go back. But maybe you're thinking, we'll build better shielding. We'll solve this problem with engineering. That's what NASA thought too, until they did the math. To properly shield a spacecraft from cosmic radiation, you'd need about 15 feet of solid lead in every direction. Do you understand what that means? The mass of such a spacecraft would be astronomical. Getting it off the ground would require so much fuel that the mission becomes physically impossible with any rocket technology we have or can envision. You can't build a spaceship thick enough to protect humans without making it too heavy to launch. Some have proposed using water as shielding, surrounding the crew compartment with tanks of it. Water is excellent at absorbing radiation. And hey, you need to bring water anyway, right? Except here's the problem. When cosmic rays hit water molecules, they don't just stop. They create secondary radiation, sometimes producing particles even more dangerous than the originals. It's like trying to stop bullets by shooting more bullets at them. The physics just doesn't work in our favor. What if I told you that the universe itself seems to be saying, stay home? That the very structure of physical law appears designed to keep biological life tethered to the worlds where it evolved? We're about to go deeper into this rabbit hole, into problems that make radiation look manageable. But first, let me ask you something. Are you still comfortable thinking of Earth as a prison? Or are you starting to see it as a sanctuary? Let's talk about your bones. Right now, they feel solid, don't they? Strong, reliable, the literal framework holding you together. You can jump, run, lift heavy objects. Your skeleton is so dependable that you never even think about it. But the moment you leave Earth's gravity, your bones begin to die. And I mean that literally. Within days of entering microgravity, your body starts cannibalizing its own skeleton at a rate of 1 to 2% bone mass per month. Think of it like this. Imagine you own a house, and one day you notice the foundation is crumbling. Not slowly, over decades, but visibly deteriorating, week by week. By the end of a year, 20% of your foundation is simply gone. That's what happens to astronauts' bones in space. Dr. Adrien Leblanc from NASA's Bone Density Laboratory spent 30 years studying this phenomenon, and his conclusion is haunting. Long-duration spaceflight results in bone loss equivalent to aging 20 to 30 years. A 6-month stay on the ISS ages your skeleton 3 decades. And here's the truly disturbing part. Even after returning to Earth, even with aggressive exercise and medical intervention, that bone never fully grows back. Scott Kelly, the astronaut who spent 340 consecutive days in space, returned with bone density loss that will never completely recover. His hip bones, his spine, his femurs, all permanently weakened. He's 45 years old with the skeleton of a 75-year-old man in those specific areas. Now imagine a 3-year mission to Mars. But bones are just the beginning of how gravity owns you. Your cardiovascular system evolved over hundreds of millions of years to pump blood against Earth's gravitational pull. Your heart works hard to send oxygenated blood up to your brain, fighting against gravity every beat. Your veins have one-way valves to prevent blood from pooling in your legs. It's an elegant system, fine-tuned by evolution to work perfectly at 1 g, Earth's gravitational acceleration of 9.8 meters per second squared. In microgravity, this system goes haywire immediately. Blood shifts from your legs to your upper body and head. Your face swells. Your sinuses feel perpetually congested. Astronauts call it puffy face syndrome, but that cute name masks something terrifying happening inside there. Skulls. Dr. Michael Barrett, a NASA flight surgeon, discovered something in 2011 that should have been front-page news everywhere. He performed eye examinations on astronauts returning from long-duration missions and found that about 40% had experienced flattening of their eyeballs due to increased intracranial pressure. Let me make sure you understand what this means. Their brains were literally being squeezed by cerebrospinal fluid that had nowhere to drain in the absence of gravity. This pressure flattened the backs of their eyeballs, causing permanent vision changes. Some astronauts who had perfect vision before spaceflight now need reading glasses. Others have visual distortions that will never go away. NASA calls this space-associated neuroocular syndrome, or SANS. I call it what it really is: evidence that human beings were never designed to function away from Earth's gravity. In 2018, Dr. Larry Kramer from the University of Texas published MRI studies showing that astronauts' brains physically change shape in space. The brain floats upward in the skull, compressing against the top of the cranial cavity. The pituitary gland, that crucial hormone regulator, gets squeezed and deformed. And here's the nightmare fuel. We have no idea what the long-term consequences of this are, because no human has ever been in space long enough for us to study it properly. Every Mars mission plan assumes astronauts will arrive with functioning brains. We can't actually guarantee that. Your muscles suffer the same fate as your bones. Despite rigorous exercise protocols, astronauts lose 20 to 30% of muscle mass during long missions. And it's not just about getting weaker. The type of muscle fiber changes. Slow-twitch endurance fibers convert to fast-twitch power fibers. Then both types atrophy. Your body is literally eating itself, reconfiguring for an environment where power and endurance are no longer relevant because there's nothing to push against. Chris Hadfield, the famous Canadian astronaut, described returning from space and trying to walk. I felt like I weighed 1,000 pounds. My legs were useless. I couldn't even carry my own body weight. But here's what will really blow your mind. We've only studied these effects in low Earth orbit, where astronauts can return to gravity in a few hours if something goes wrong. Mars is a 40 million mile journey one way. If we send people there and discover that the combination of prolonged microgravity during transit and Mars' 1/3 gravity on the surface causes irreversible damage we haven't predicted, we can't just bring them home. They're committed. They're stuck. And they might be dying. In 2019, Dr. Peter Norsk from ESA published a comprehensive review of cardiovascular deconditioning in space. His team found that the heart itself shrinks in microgravity. It becomes more spherical, less efficient. The walls thin out. Blood vessels lose their ability to constrict properly. When astronauts stand up after landing, their blood pressure can drop so dramatically that they faint. Their bodies have forgotten how to function in gravity. Now imagine forgetting for 3 years during a Mars mission, then trying to readapt to even Mars's partial gravity, while simultaneously dealing with radiation damage, bone loss, and muscle atrophy. There's a phenomenon NASA doesn't like to publicize called orthostatic intolerance. After returning from space, many astronauts cannot stand for more than a few minutes without their heart rate spiking to dangerous levels and their blood pressure collapsing. Some require months of reconditioning. Some never fully recover their ability to stand for extended periods. Michael Lopez Alegria, who spent 7 months on the ISS, described his return. "I felt like I was going to pass out every time I stood up for weeks afterward. My body had completely forgotten what gravity felt like." Think about this. The longest any human has spent in space continuously is 437 days. Russian cosmonaut Valery Polyakov achieved this in 1994-1995 aboard Mir. When he returned to Earth, he could barely walk. He required extensive physical therapy. And that was in low Earth orbit, where Earth's gravity is still about 90% of surface strength, and where help was always just 3 hours away. A Mars mission would be longer, much longer, and help would be impossible. Here's the question nobody wants to answer. What happens to a human body after 3 years in space? After 5 years? After 10? We don't know. We literally cannot know without sending people on those missions. And if the answer is, the damage becomes irreversible and fatal, we'll discover that truth by watching astronauts die slowly, millions of miles from home, while Mission Control watches helplessly from Earth with a communication delay of up to 22 minutes one way. You want to know something really disturbing? Astronauts on the ISS are healthier than they would be on a Mars mission for one critical reason. They have gravity to return to within hours. If a medical emergency occurs, if the bone loss becomes critical, if the cardiovascular deconditioning threatens their life, they get in a Soyuz capsule and they're back in Earth's gravity in 3 hours. That safety net disappears completely for Mars. There is no coming home early. There is no abort option halfway through. You're committed for years. But let me show you something even more fundamental about why gravity owns us. Your inner ear, those tiny semicircular canals filled with fluid and hair cells, evolved to sense Earth's gravity. They tell your brain which way is up. They maintain your balance. They prevent you from getting dizzy. In microgravity, they become useless. Your brain receives no gravitational input. This is why about 50% of astronauts experience space motion sickness during their first few days in orbit. Nausea, vomiting, disorientation. Their brains are screaming, something is fundamentally wrong. Because something is fundamentally wrong. Most adapt after a few days. But here's the horrifying part. They adapt by essentially learning to ignore their vestibular system. They rewire their neural pathways to function without gravitational input. Then, when they return to Earth, they have to rewire again. Some astronauts report feeling disoriented and dizzy for weeks after landing. They'll be walking and suddenly feel like they're falling. They'll try to set something down and miss the table because their spatial awareness is broken. Their brains have to relearn the most basic assumption of existence, that noun exists. Now imagine doing this twice, spending years between adaptations. On Mars, where gravity is different from both Earth and microgravity, your brain would need to adapt 3 times. To microgravity during the outbound flight, to Mars gravity, then back to microgravity for the return, and finally to Earth gravity. Each transition risks permanent neural damage, permanent spatial disorientation, permanent loss of balance. We're talking about astronauts who might never be able to walk straight again, whose brains might never properly process 3-dimensional space again. Are you starting to see it? Gravity isn't just a force we experience. It's woven into every cell, every system, every function of our bodies. We aren't just living on Earth. We are Earth. Our bodies are shaped by it, defined by it, utterly dependent on it in ways so profound that we only notice when we try to leave. And what we notice is that we're dying. Slowly, systematically, in every measurable way. Dying. Let's talk about something you take for granted every single second of every single day. Your immune system. Right now, as you watch this, an army of white blood cells is patrolling your bloodstream, hunting for threats. T cells, B cells, natural killer cells, all working in perfect coordination to keep you alive. This system is so sophisticated, so finely tuned, that it can distinguish between thousands of different pathogens, remember infections from decades ago, and mount targeted responses to threats it's never encountered before. It's a miracle of evolution, 4 billion years in the making. In space, it stops working. Not completely, but enough to terrify anyone who understands immunology. Dr. Clarence Sams from NASA's Space Biosciences Division published research in 2013 that revealed something shocking. Astronauts' T-cell function decreases by up to 50% in microgravity. 50%. Your body's ability to fight infections is literally cut in half the moment you leave Earth's gravity. Think of it like this. Imagine your home security system suddenly only detecting half the burglars trying to break in. How safe would you feel? But it's not just a numbers problem. The T cells that remain active start behaving erratically. Dr. Millie Hughes Fulford, who flew on a space shuttle mission and later became an immunologist, discovered that T cells in microgravity lose their ability to activate properly. The molecular signals that tell them, attack this pathogen, get scrambled. The cells become confused, sluggish, ineffective. It's like having security guards who not only can't see half the threats, but who also forgot what threats look like. Herpes viruses, those dormant infections that live in your nerve cells, waiting for your immune system to weaken, reactivate in about half of all astronauts during spaceflight. Chickenpox, shingles, cold sores, all coming back because your immune system can no longer keep them suppressed. These aren't just inconveniences. Shingles in particular can cause nerve damage, chronic pain, even blindness if it affects the eyes. Now imagine dealing with a shingles outbreak while wearing a spacesuit, millions of miles from medical care, in an environment where you can't even scratch the affected area without removing protective equipment. In 2014, Dr. Satish Mehta from NASA's Johnson Space Center published a study that found herpes viruses in bodily fluids from astronauts during and after spaceflight in numbers hundreds of times higher than normal. The dormant viral loads that your healthy Earth-based immune system keeps at undetectable levels suddenly explode when you go to space. And here's the terrifying implication. If dormant viruses reactivate this aggressively, what happens when you encounter a new infection in space? Think about this scenario. You're on Mars. One of your crewmates develops a respiratory infection. Maybe they brought it from Earth, some bacteria that was lurking dormant, waiting. On Earth, your immune system would fight it off in a week or two. In space, with your immune function crippled, that infection becomes life-threatening. And it's not just threatening to the infected person. In the closed environment of a spacecraft or habitat, infections spread instantly. Everyone gets exposed. Everyone gets sick, and everyone has only half an immune system to fight it with. We saw a preview of this nightmare during the Apollo 7 mission in 1968. Commander Wally Schirra developed a cold during the flight. Within days, all 3 crew members were infected. In the close quarters of the spacecraft, there was no escape. The mission became a misery of congestion, headaches, and irritability. That was 11 days in space. A Mars mission is 3 years. If COVID-19 has taught us anything, it's that respiratory viruses in close quarters are catastrophic. Now imagine that scenario with no ability to isolate, no hospital to go to, and immune systems operating at half capacity. But the immune system dysfunction goes deeper, literally deeper, into your cells. In 2019, Dr. Afshin Beheshti from NASA's Genelab analyzed gene expression data from astronauts and found something that should have stopped all Mars planning immediately. Spaceflight fundamentally alters how thousands of genes turn on and off in your cells. Genes involved in DNA repair, cell growth, metabolism, all showing abnormal expression patterns. Your cells are literally forgetting how to be cells, losing the molecular programs that keep them functioning properly. What if I told you that this isn't random? That these specific systems, immune function, bone density, muscle mass, cardiovascular health, they all rely on gravitational signaling at the cellular level? In 2017, Dr. Mary Book-Singh from Harvard Medical School discovered something extraordinary. She found that bone cells have mechanoreceptors, specialized proteins that sense physical stress and strain. When you walk, when you stand, when gravity pulls on your skeleton, these receptors detect it and signal the cell to maintain bone density. In microgravity, those signals stop. The cells essentially think, we don't need to be strong anymore, and begin dismantling themselves. The same principle applies throughout your body. Muscle cells sense loading through similar mechanoreceptors. Cardiovascular cells respond to the pressure gradients created by pumping blood against gravity. Even immune cells are influenced by the physical environment created by normal gravitational conditions. Take that away, and you're not just removing a force. You're removing a fundamental signal that tells your cells how to function. It's like deleting half the instruction manual for being alive. Here's what really blows my mind. We evolved in Earth's gravity field for billions of years. Not millions, billions. Every single adaptation that makes us human, from bipedalism to our enlarged brains, to our opposable thumbs, all of it happened under constant gravitational selection pressure. Organisms that couldn't handle gravity didn't survive to reproduce. Organisms that thrived in gravity passed on their genes. We are the product of 4 billion years of optimization for exactly one gravitational field, 9.8 meters per second squared. Think of it like a fish again, but more extreme. A fish isn't just adapted to water, it's adapted to the specific pressure at the specific depth where its species lives. Take a deep-sea fish to the surface, and it literally explodes as the lower pressure allows gases in its body to expand. Take a surface fish to the deep ocean, and it gets crushed by the pressure. These aren't weaknesses. These are the inevitable results of optimization for specific conditions. We are deep-sea organisms adapted to one specific depth, sea level on Earth at 1G. In 2020, the COVID-19 pandemic gave us an unintentional experiment in immune system function. Astronauts on the ISS were some of the only humans completely isolated from the virus. But when supply ships arrived, NASA implemented unprecedented sterilization procedures because they absolutely knew, that if that virus reached the station, the astronauts would be extraordinarily vulnerable. Their compromised immune systems in the closed environment of the station would turn what might be a mild infection on Earth into a potential mission-ending catastrophe. They were more afraid of a respiratory virus than they were of the vacuum of space. Let that sink in. Now multiply that fear by 3 years. Add the radiation exposure we talked about earlier, which further damages immune function. Add the stress of isolation, which suppresses immunity even more. Add the fact that wounds heal slower in space, that infections are harder to treat, that antibiotics may not work as effectively because bacterial behavior changes in microgravity. You end up with a situation where a simple cut could become septic, a minor infection could become fatal, and help is 40 million miles away. Dr. Dwayne Pearson, NASA's chief microbiologist, studied bacteria in space and found they become more virulent, more resistant to antibiotics, and grow faster in microgravity. Evolution doesn't stop in space. It accelerates. Bacteria reproduce every 20 minutes, adapting to their environment with terrifying speed. In the closed ecosystem of a spacecraft, you're creating a perfect laboratory for evolving superbacteria specifically adapted to kill immune-compromised hosts. You become both the petri dish and the victim. There's something else nobody talks about. The psychological stress of long-duration spaceflight further suppresses immune function. Chronic stress floods your body with cortisol, which directly inhibits immune cell production and function. Astronauts on Mars missions will experience stress levels beyond anything we've studied. The isolation, the danger, the knowledge that rescue is impossible, all of it combining to create a state of chronic psychological stress that will devastate whatever immune function they have left. Their bodies will be fighting a war on multiple fronts: radiation, microgravity, pathogens, and their own stress hormones, all at once. Are you starting to understand why this might be impossible? Not hard, not challenging, but fundamentally impossible? We're not talking about engineering problems that can be solved with better technology. We're talking about biological constraints that are written into the source code of life itself. Gravity isn't just where we live, it's how we live. It's what we are. And trying to live without it is like trying to be a different species. Let's go deeper. Let's talk about something that sounds science fiction, but is horrifyingly real. Space itself is changing astronauts' DNA, not in some vague, hand-wavy way. I mean literal, measurable changes to the genetic code that makes you who you are. In 2019, NASA published the results of the twins study, and it should have been the biggest science story of the decade. They studied identical twins Scott and Mark Kelly. Scott spent 340 days on the ISS, while Mark stayed on Earth. When Scott returned, they compared his genetic profile to his twin brothers. What they found was shocking. 7% of Scott, Kelly's genes had changed expression patterns and hadn't returned to normal even after 6 months back on Earth. 7%. Do you understand what that means? Hundreds of genes that control everything from immune function to cell repair to metabolism were now behaving differently than they did before spaceflight. And this wasn't temporary adaptation. This was permanent alteration. Dr. Christopher Mason from Weill Cornell Medicine, who led the study, used a phrase that still gives me chills. Space left its mark on him at the genetic level, but it gets worse, much worse. They found elongation of telomeres during spaceflight. Telomeres are the protective caps on the ends of your chromosomes, and their length is directly related to aging and cancer risk. Longer telomeres sound good, right? Wrong. The sudden elongation followed by rapid shortening after returning to Earth creates exactly the kind of genetic instability that leads to cancer. Scott Kelly's cells experienced more genetic stress from 1 year in space than most people experience in a lifetime on Earth. Chromosomal inversions, deletions, and translocations all increased during spaceflight. These are the same types of mutations we see in cancer cells. Dr. Elia Overby, another researcher on the study, put it bluntly. We saw things we did not expect and cannot fully explain. The human body is being pushed to its absolute limits in space, and the genome is responding in ways that concern us. Now let me introduce you to something called cosmic ray hits. Individual particles of radiation passing through your body and striking your DNA. On Earth, our magnetic field deflects most of these. In space, you're getting hit constantly. Dr. Francis Cucinoda, who we mentioned earlier, calculated that during a Mars mission, every cell nucleus in your body will be traversed by a proton or heavier ion approximately once every 3 days. Every cell, every 3 days. For 3 years. Think of your DNA as a computer hard drive with your life's operating system. Now imagine someone shooting that hard drive with a gun every 3 days for 3 years. Sure, the computer might keep working for a while. Data redundancy, error correction, repair mechanisms might compensate for some damage. But eventually, critical files get corrupted. Programs start glitching. The whole system becomes unstable. That's what's happening to astronauts' DNA in space. In 2012, Dr. Megumi Hata from NASA's Space Radiation Laboratory, PUBLISHED, research showing that a single high-energy cosmic ray passing through a cluster of cells can damage all of them simultaneously. It's not like regular radiation, where you might get hit randomly. These particles have so much energy that they create tracks of destruction through tissue, damaging every cell on their path. She called these microlesions, but that's a gentle name for what's essentially a microscopic bullet wound through your organs. Here's what will blow your mind. We can simulate every other aspect of spaceflight on Earth. We have underwater neutral buoyancy labs that simulate weightlessness for training. We have centrifuges that simulate high G forces. We have isolation chambers for psychological studies. But we cannot simulate the cosmic radiation environment of deep space. The particles are too energetic, too varied, too constant. Every astronaut who ventures beyond Earth's magnetic field is a test subject in an experiment we can't rehearse. The most terrifying part? DNA damage is cumulative. It adds up. Every hit increases your cancer risk, your risk of genetic diseases, your risk of passing mutations to future children. Scott Kelly, who spent 340 days in space total across multiple missions, has received a radiation dose that increases his lifetime cancer risk by about 3%. A Mars mission would give you double that dose. And if you wanted to establish a permanent presence on Mars, if you wanted to stay there, you'd be accumulating that damage year after year after year. But let's talk about something even more disturbing. Epigenetic changes. These are modifications that don't change the DNA sequence itself, but alter how genes are expressed. Dr. Sem Maiden from Weill Cornell found that astronauts show changes in DNA methylation patterns, the chemical tags that turn genes on and off. These changes affect genes involved in oxygen deprivation response, immune system regulation, and DNA repair itself. Your body is not just getting damaged, it's losing the ability to fix the damage. In 2021, Dr. Silvana Martino from the Italian Space Agency discovered something that connects everything we've talked about. She found that spaceflight creates a state called oxidative stress throughout the body. Free radicals, those destructive molecules you've heard about in antioxidant commercials, increase dramatically in space. They attack everything: DNA, proteins, cell membranes. It's like your body is rusting from the inside out. And the sources of this oxidative stress? Radiation, microgravity-induced inflammation, disturbed sleep cycles, psychological stress, all combining into a perfect storm of cellular destruction. Think of it like this. Imagine your body as a city, and the infrastructure maintenance crews are your DNA repair mechanisms. Normally, they can keep up with the damage from daily wear and tear. But in space, it's like the city is being hit by constant small earthquakes. The maintenance crews are working overtime, getting exhausted, making mistakes. Eventually, buildings start collapsing. That's your cells dying or becoming cancerous. Roads become impassable. That's your systems failing. And the city itself begins to change in response, tearing down unused buildings, converting others to emergency shelters. That's your genetic expression changing permanently. What if I told you that we've known about these problems for decades and we've been hoping we could ignore them? That the bright, optimistic vision of human space colonization has always been running away from the dark reality of biology? In 1964, Soviet cosmonaut Alexei Leonov became the second human to walk in space. He nearly died. His suit ballooned in the vacuum, and he couldn't fit back through the airlock. He had to partially depressurize his suit, risking death by decompression, to squeeze back inside. When he returned to Earth, he said something profound. Space is not indifferent to us. It is actively hostile. He meant the mechanical dangers, the vacuum, the temperature extremes, the radiation. But he was more right than he knew. Space is hostile at every level, from the cosmic scale down to the molecular. It attacks your DNA, your cells, your tissues, your organs, your systems, your mind, and it never stops. There is no shelter from it. There is no armor thick enough. There is no medicine that can prevent it. Dr. Peter Ward, a paleontologist from the University of Washington, proposed something called the Medea hypothesis. It's a dark twist on the Gaia hypothesis, which suggests Earth is a self-regulating system that maintains conditions suitable for life. Ward argues that life isn't just passive. It's actively constrained to specific conditions by the physics and chemistry of existence. Life didn't conquer Earth despite the conditions. Life exists because the conditions were perfect. Change those conditions, even slightly, and life fails. Not struggles, fails. We see this in the fossil record. Every mass extinction event correlates with changes in atmospheric composition, temperature, or radiation levels. Life is fragile, not because it's weak, but because it's optimized. A Formula One race car is the fastest vehicle on Earth, but only on a smooth racetrack. Take it off-road, and it disintegrates. We are that race car. Earth is our track. Space is off-road. And here's the final devastating truth about genetic damage. We won't know the full extent for generations. Mutations can be silent, lurking in your genome, only manifesting when they're passed to children. The children of astronauts might be at increased risk for genetic diseases. Their children might be at even higher risk. We're talking about potentially creating a genetic underclass of space-damaged humans whose descendants carry the scars of their ancestors' cosmic exposure. The children of Hiroshima and Nagasaki survivors showed increased rates of genetic disorders. That was from a single acute radiation exposure. Imagine the cumulative effect of years of chronic exposure to cosmic radiation. Imagine trying to have healthy children on Mars, where every fetus is being irradiated constantly, where every DNA replication carries an increased risk of error, where evolution itself is being accelerated by radiation, but not in any direction we'd want. We cannot escape our biology. We cannot willpower our way past physics. We cannot engineer ourselves into creatures capable of surviving in space, not without becoming something that isn't human anymore. And maybe that's the real question we need to ask. How much of ourselves are we willing to destroy in the attempt to leave? Now let's talk about something you've probably never considered, your gut bacteria. Right now, your intestines contain about 100 trillion bacterial cells, outnumbering your human cells by a factor of 10 to 1. These aren't parasites, they're partners. They produce vitamins your body can't make. They train your immune system. They produce neurotransmitters that affect your mood and cognition. They break down food into nutrients you can absorb. Without them, you would die. With the wrong ones, you also die. This ecosystem, called your microbiome, evolved over millions of years in Earth's gravity. In space, it goes insane. Dr. Hernan Lorenzi from the J. Craig Venter Institute published research in 2019 that revealed something terrifying about the microbiome in space. The bacterial composition of astronauts' guts shifts dramatically during spaceflight. Beneficial bacteria that produce short-chain fatty acids and vitamins decrease. Opportunistic pathogens like Enterobacterius increase. Your gut ecosystem isn't adapting to space. It's collapsing and being replaced by something more aggressive, more inflammatory, more dangerous. Think of it like this. Imagine a peaceful forest where predators and prey exist in balance. Now remove a fundamental force that maintained that balance, say, the seasonal cycles. The ecosystem doesn't just adjust, it crashes. Aggressive species that can tolerate the new conditions take over. Diversity plummets. The forest becomes something unrecognizable, hostile to most of its original inhabitants. That's your gut in space. And here's the nightmare. This isn't happening in isolation. Your gut bacteria communicate directly with your brain through the vagus nerve. They influence everything from your mood to your decision-making to your stress response. In 2017, Dr. Fred Turek from Northwestern University demonstrated that disrupting the microbiome in mice caused cognitive impairment, anxiety, and depressive behaviors. The mice looked physically healthy, but their brains weren't working right because their gut bacteria were wrong. Now imagine astronauts on a Mars mission, already dealing with radiation damage, bone loss, and immune suppression, also experiencing cognitive decline because their microbiome has been replaced by an alien ecosystem that their brains can't properly communicate with. How do you make life or death decisions when your gut bacteria are literally making you anxious and depressed? But it gets worse, way worse. In 2018, Dr. Cheryl Nickerson from Arizona State University made a discovery that should have been classified for national security reasons. She found that bacteria become more virulent in microgravity. Salmonella, grown aboard the space shuttle, became 3 times more lethal to mice than genetically identical bacteria grown on Earth. 3 times. The bacteria didn't mutate. They just expressed different genes in response to microgravity, genes that made them better at infecting hosts, better at forming biofilms, better at resisting antibiotics. Let me make sure you understand the implications. Every surface of a spacecraft becomes a breeding ground for superbacteria, specifically adapted to kill you in space. Your own gut bacteria are becoming more aggressive. The bacteria you brought from Earth to Mars are evolving in real time to exploit your weakened immune system. And there's no way to sterilize a spacecraft completely without also sterilizing yourself. You are the contamination. Your body is the vector. You can't escape it because it's part of you. NASA found fungus growing behind panels on the ISS in places that should have been impossible to access. Aspergillus penicillium, species that can cause serious lung infections, thriving in the spacecraft's life support systems. Astronauts are breathing these spores constantly. On Earth, your healthy immune system would clear them easily. In space, with your immune function cut in half, every breath is a potential infection. The ISS is only 20 years old, and it's already developing its own ecosystem of spacecraft-adapted microorganisms. Imagine what a Mars habitat would look like after 10 years, 20 years, 50 years. Here's something that will blow your mind. Biofilms. Bacteria in space form biofilms, those slimy protective layers, much faster and thicker than on Earth. Dr. Cynthia Collins from Rensselaer Polytechnic Institute found that in microgravity, biofilms grow to be 3-dimensional structures rather than flat mats. They become columnar, like towers, increasing surface area and making them exponentially harder to remove. These biofilms can clog filters, corrode metal, contaminate water supplies, and harbor pathogenic bacteria protected from antibiotics and disinfectants. On Earth, gravity helps liquids drain. Biofilms eventually get washed away. In space, there's no drainage. The biofilm just grows and grows, spreading across surfaces, into crevices, through ventilation systems. The ISS has a constant battle against biofilm formation, requiring hours of crew time each week for cleaning and maintenance. Now imagine a Mars mission where water is scarce, where you can't afford to waste it on excessive cleaning, where the biofilms slowly take over your habitat from the inside. Think about this scenario. You're on Mars, and your water recycling system, which you absolutely depend on for survival, starts malfunctioning because biofilms have clogged the membranes. You can't just replace the system. You brought limited spare parts on a multi-million-mile journey. You can try to clean it, but that requires water, the very resource you're running out of. You're trapped in a death spiral, where the solution requires the resource you're trying to save. And meanwhile, you're inhaling fungal spores. Your gut bacteria are making you depressed, and your immune system is too weak to fight any of it. In 2020, Dr. Kasturi Venkateswaran from NASA's Jet Propulsion Laboratory identified dozens of bacterial species on the ISS that were previously unknown to science. They didn't come from Earth, or rather, they did, but they've evolved so rapidly in the unique environment of the space station that they're effectively new species. 20 years. That's all it took to create novel organisms specifically adapted to live in spacecraft. Evolution doesn't pause for human convenience. And evolution in a closed environment with stressed hosts and constant selection pressure happens frighteningly fast. What if I told you that your body is not a single organism but a superorganism? A coalition of trillions of entities that only work together under very specific conditions? On Earth, with Earth's gravity, with Earth's day-night cycle, with Earth's atmospheric pressure, this coalition maintains itself. In space, the coalition starts to fracture. Different members start pursuing their own survival strategies. The unity of you begins to dissolve at the microscopic level. Your circadian rhythm, that 24-hour cycle that regulates everything from sleep to hormone production to DNA repair, is controlled partially by gut bacteria. They have their own circadian rhythms that synchronize with yours. In space, where there's a sunrise every 90 minutes on the ISS, where light and dark lose meaning, where your body's clock becomes confused, your gut bacteria's clocks also become desynchronized. Dr. Martha Vita Turner from Northwestern University found that disrupted circadian rhythms in the microbiome lead to metabolic syndrome, weight gain, inflammation, and accelerated aging. Your bacteria are literally timing out of sync with your cells, creating chaos in the system. Sleep itself becomes nearly impossible. Astronauts on the ISS sleep an average of 6 hours per night compared to 7 or 8 on Earth, not because they don't want to sleep, but because their bodies can't figure out when to sleep. Melatonin production becomes irregular. REM sleep decreases. Deep sleep fragmentation increases. Dr. Charles Czeisler from Harvard Medical School studied astronauts' sleep patterns and concluded that chronic sleep deprivation in space creates cognitive impairment equivalent to being legally drunk. You're trying to operate complex machinery, make critical decisions, and stay alive in the most hostile environment imaginable, while cognitively impaired to the level of intoxication. For years. And sleep deprivation suppresses immune function even further. It disrupts the microbiome even more. It impairs DNA repair mechanisms. It's another positive feedback loop of biological collapse, where each problem makes every other problem worse. You can't sleep because your circadian rhythm is broken. Your circadian rhythm is broken because your microbiome is dysregulated. Your microbiome is dysregulated because your immune system is suppressed. Your immune system is suppressed because you can't sleep. Round and round, spiraling downward. Here's the truly disturbing part. NASA knows all of this. Every space agency knows all of this. The research exists. The papers are published. The data is clear. And yet the Mars mission planning continues, with optimistic timelines and cheerful animations of astronauts bounding across the Martian surface. Why? Because the alternative, admitting that human beings might be fundamentally incompatible with space, is too devastating to contemplate. It means accepting limits. It means giving up the dream. It means admitting that the universe doesn't want us, and we can't change its mind. Dr. Nathaniel Schuchik from the University of Nottingham studied worms in space and found that microgravity affects their development at the most fundamental level. The worms could survive, but they couldn't develop properly. Their muscles formed incorrectly. Their neurons connected wrong. These are simple organisms with only 1,000 cells total, and space broke their developmental programs. Now extrapolate that to humans with trillions of cells, and you begin to understand why the idea of reproducing in space, of raising children on Mars, might be a biological impossibility. No human has ever been conceived, gestated, or born in space. We have no idea if it's even possible. Studies with rodents suggest it's not. Pregnant rats in space showed increased fetal resorption, developmental abnormalities, and stillbirths. The embryos couldn't develop properly without gravitational cues. The mother's bodies, stressed by spaceflight, couldn't maintain the pregnancy, and these were short-duration experiments. Imagine 9 months of human gestation in microgravity, or even Mars's partial gravity. Imagine a fetus trying to develop bones that won't experience full gravity until after birth. Imagine a developing brain trying to wire itself without vestibular input. What would even be born? The microbiome transfers from mother to child during birth. The vaginal and gut bacteria colonize the newborn, establishing its immune system and metabolic profile. In space, that microbiome is wrong, dysregulated, colonized by opportunistic pathogens. What happens to a child who receives a dysregulated microbiome at birth? What happens to their immune system development, their cognitive development, their entire physiological foundation? We don't know, and the experiments necessary to find out would be unethical. Think about this. Every mammal on Earth experiences fetal development in gravity. The positioning of organs, the formation of the vestibular system, the loading of bones and muscles, all of it happens with constant gravitational input. Remove that input, and you're not just conducting an experiment. You're potentially creating a human being who is fundamentally different, possibly disabled, certainly unprecedented. And you're doing it 40 million miles from any medical facility that could help. We're talking about biological constraints so fundamental that they might be insurmountable with any technology we can envision. Not difficult to overcome. Insurmountable. The difference matters. Difficult means it takes longer, costs more, requires innovation. Insurmountable means there is no solution, only acceptance of limits. And right now, all the evidence points toward the latter. Let's shift gears and talk about something more tangible: logistics. Because even if we solved every biological problem I've mentioned, even if we discovered some miracle treatment that kept astronauts healthy in space, we'd still face an insurmountable wall of mathematics and physics. Let me show you why getting to Mars might be the easy part, and staying alive there might be physically impossible. A human being needs about 2 kilograms of water per day just for drinking. That's 730 kilograms per person per year. A crew of 6 on a 3-year mission needs 13,140 kilograms of water. That's 13.1 metric tons, just for drinking. Now add water for hygiene, for growing food, for cooling systems, for producing oxygen through electrolysis. You're looking at closer to 100 metric tons of water for the mission. The space shuttle could carry about 10 metric tons to orbit. You'd need 10 shuttle launches just to deliver the water. And that's before you've sent any actual equipment, habitat modules, or the crew themselves. Think of it like this. Imagine you're planning a camping trip, but you can only carry what fits in a small backpack, and the campground is 3 years away by car, with no stops allowed. Every item you bring must be worth its weight multiple times over, because weight equals fuel, equals cost, equals feasibility. Now multiply that constraint by 1,000, because we're not talking about a car trip. We're talking about fighting against Earth's gravity well to reach orbital velocity of 28,000 kilometers per hour, then accelerating even more to reach Mars. Dr. Robert Zubrin, one of the most optimistic Mars mission advocates, proposed the Mars Direct Plan in the 1990s, even his stripped-down, minimalist approach required launching 120 metric tons to Mars. To put that in perspective, the Saturn V rocket, the most powerful rocket ever built, could launch 140 metric tons to low Earth orbit, but only 48 metric tons on a trajectory to the Moon. Mars is much farther. The rocket required to launch 120 tons to Mars would be at least twice as powerful as the Saturn V. We don't have such a rocket. We have never built such a rocket. And every kilogram of payload requires exponentially more fuel because you have to lift not just the payload, but also the fuel needed to lift the fuel. This is called the tyranny of the rocket equation, discovered by Konstantin Tsiolkovsky in 1897. The math is brutal and unforgiving. To increase your final velocity, you need more fuel. But that fuel has mass, so you need even more fuel to lift it, which has mass, so you need even more fuel to lift that. It compounds exponentially. There's a fundamental limit to how much payload you can deliver to deep space with chemical rockets, and we're already pushing against that limit. In 2016, SpaceX announced plans for the Interplanetary Transport System, later renamed Starship, designed to carry 100 tons to Mars. The engineering challenges are staggering. The vehicle requires in-orbit refueling, meaning multiple launches to fill the tanks before the Mars transfer. Current estimates suggest 5 to 10 refueling launches for a single Mars mission. If any of those launches fail, the mission fails. The complexity multiplies with each additional launch. The failure probability compounds. But let's say we solve the launch problem. Let's say we get everything to Mars. Now you need to keep humans alive on a planet that is actively trying to kill them. The Martian atmosphere is 95% carbon dioxide with a surface pressure of about 0.6% of Earth's. You cannot breathe it. You cannot go outside without a pressure suit. The temperature averages minus 60 degrees Celsius and can drop to minus 125 degrees at the poles. Water exists only as ice or vapor, never liquid at the surface, because the pressure is below water's triple point. Dr. Chris McKay from NASA's Ames Research Center spent his career studying Mars habitability. His conclusion is stark. Mars is not a second Earth. It's a fundamentally different world that is hostile to life at every level. The soil contains perchlorates, toxic chemicals that would poison any plants we try to grow. The lack of magnetic field means surface radiation levels are about 50 times higher than on Earth. Even underground, you're exposed to radiation that penetrates meters of rock. There is nowhere safe on Mars. Nowhere. Growing food on Mars is the fantasy that refuses to die. The movie The Martian popularized the idea of growing potatoes in Martian soil. Here's the reality. Martian regolith is not soil. Soil is a complex ecosystem of minerals, organic matter, and billions of microorganisms. Regolith is sterile, toxic dust. To grow anything, you'd need to import soil from Earth, which brings us back to the mass problem. Or you'd need to create soil, which takes years of composting and biological activity. Even then, the plants would be constantly bombarded by radiation and would need supplemental lighting because Mars receives only 43% of the sunlight that Earth does. Dr. Uyghur Wanling from Wageningen University conducted experiments growing crops in simulated Martian soil. The plants grew barely, but accumulated toxic levels of heavy metals from the regolith. They would be poisonous to eat without extensive processing. The energy cost of growing food on Mars, including the habitat pressurization, heating, lighting, and soil processing, would be enormous. It would be more efficient to bring all food from Earth, but that brings us back to the mass problem. Here's a number that will blow your mind. A single astronaut requires about 2,000 kilograms of food per year. That's assuming freeze-dried, calorie-dense food with minimal packaging. 6 astronauts for 3 years need 36,000 kilograms of food. That's 36 metric tons, just for food. Add in water, spare parts, medical supplies, scientific equipment, tools, habitat modules. power generation systems, communication equipment, and you're looking at hundreds of metric tons that need to reach Mars. The largest payload ever soft-landed on Mars was the Curiosity rover at 900 kilograms. We'd need to land payloads hundreds of times heavier while keeping them intact and functional. The landing itself is another impossibility masquerading as an engineering challenge. Mars's thin atmosphere provides some aerobraking, but not enough to slow a heavy payload to safe landing speeds with parachutes alone. You need retro rockets, which means carrying fuel all the way from Earth, which means even more mass at launch, which means an even bigger rocket, which compounds the tyranny of the rocket equation even further. In 2012, NASA's Mars Science Laboratory mission, which landed Curiosity, used a sky crane system that lowered the rover to the surface on cables while hovering rockets fought against gravity. It was an engineering marvel. It worked once with a 900-kilogram payload. Scaling that system up by a factor of 100 or more introduces failure modes we haven't even imagined. One malfunction, one unexpected wind gust, one sensor error, and your entire habitat crashes into the surface at hundreds of kilometers per hour. Mission over. Crew dead. Think about this scenario. You've made it to Mars. You've landed safely, which is already a miracle. Now you're living in a habitat the size of a small house with 5 other people for the next year and a half, before the launch window to return to Earth opens. You cannot go outside without a 2-hour suiting up procedure. When you do venture out, you're wearing a bulky pressure suit that makes every task exhausting. A simple geological survey that would take an hour on Earth takes all day on Mars. You're constantly tired from the exertion, the low gravity, the radiation, the stress. Something breaks. Maybe it's a seal in the habitat's airlock. Maybe it's a pump in the water recycling system. You can fix it, but you need a specific part. You check the inventory. You don't have it. The part wasn't considered critical enough to include in the mission manifest. Without it, the system fails completely in a week. You have 2 choices. Try to fabricate a replacement with limited tools and materials, or accept that your mission just became a survival situation. This isn't a hypothetical. This is the reality of living 140 million miles from the nearest hardware store. Dr. Pascal Lay from the Mars Institute has led simulation missions in the Arctic, the most Mars-like environment on Earth. His teams have repeatedly encountered scenarios where equipment failure would have been fatal if they were actually on Mars. A broken drill, a contaminated water supply, a medical emergency. On Earth, these are inconveniences. In the Arctic, with support just a radio call away, they're serious problems. On Mars, they're potential death sentences. The psychological toll of knowing that any mistake could kill you, that help is impossible, that you're committed for years, regardless of what goes wrong. This has never been studied at the necessary duration because we've never subjected humans to it. The longest isolation studies on Earth last about a year can take place, with the knowledge that you can leave if you really need to. Mars removes that safety valve. You're locked in. The psychological pressure could break even the most stable individuals. In 2010, the Mars 500 project simulated a Mars mission with 6 crew members in isolation for 520 days. Multiple crew members developed depression. Sleep disorders became universal. Interpersonal conflicts escalated. And they knew it was a simulation. They knew they were in Russia, not on Mars. They knew they could leave in an emergency. Remove that knowledge, add the real danger, triple the duration, and you have a recipe for psychological collapse. What if I told you that all of this, every challenge I've described, assumes that nothing goes wrong? The moment something unexpected occurs, the moment you encounter a problem that wasn't anticipated in the planning, the entire mission becomes a desperate improvisation with lives hanging in the balance. And in space, things always go wrong. Always. The question isn't if, it's when and how bad. Now let's talk about energy. because nothing on Mars works without it, and getting energy on Mars is brutally difficult. On Earth, we're surrounded by energy sources. The sun shines brightly, wind blows, rivers flow, fossil fuels are abundant. Mars has none of this. The sun is dimmer. There's no wind strong enough to generate power because the atmosphere is too thin. There's no liquid water, no fossil fuels, no trees to burn. You're on an energy-starved world, and every system keeping you alive needs constant power. Solar panels seem like the obvious solution, right? They work on Earth, they work on the ISS. They should work on Mars, except Mars receives about 43% of the solar energy that Earth does, and that's at the equator, noon on a clear day. But Mars has global dust storms that can block out the sun for months. In 2018, a dust storm killed the Opportunity rover by covering its solar panels. The rover went dark and never woke up. Now imagine you're relying on solar power to produce oxygen, heat your habitat, recycle water, and power your life support systems when a dust storm hits. You have days, maybe weeks of battery backup at most. Then what? Dr. Robert Brown from Georgia Tech calculated that a human Mars mission would require about 40 kilowatts of continuous power just for basic life support. That's about 40 typical American homes worth of electricity running 24/7. To generate that with solar panels on Mars, you'd need about 200 kilowatts of panels to account for nighttime, dust, and inefficiency. That's a solar array the size of a football field. The mass would be enormous. The deployment would take weeks. Any damage to the panels from dust abrasion, meteorite impacts, or equipment failure reduces your margin for survival. Nuclear power is the alternative, but it comes with its own nightmare logistics. The multi-mission radioisotope thermoelectric generator that powered Curiosity produces about 110 watts. You'd need 400 of them to power a human mission. That's not feasible. A larger nuclear reactor could work, but it would need to be launched from Earth, landed safely on Mars, assembled and activated, all without any malfunction. If something goes wrong with the reactor, you don't just lose power. You potentially contaminate your landing site with radiation, making it uninhabitable. In 2018, NASA's Kilopower project tested a small fission reactor designed for Mars missions. It produced 10 kilowatts, a quarter of what you'd need for basic survival. To get enough power, you'd need multiple reactors, which multiplies the mass, complexity, and failure points. And nuclear fuel doesn't last forever. The reactor has a limited lifespan, maybe 10 years. After that, you need to replace it or abandon the base. Think of energy like oxygen. You don't think about breathing until you can't. On Earth, we don't think about energy because it's everywhere. On Mars, you'd be constantly aware that every action consumes power from a finite, difficult-to-replenish supply. Using a computer, heating water, turning on a light, all of it drains your survival margin. The mental burden of that constant calculation, that awareness of scarcity, would be psychologically crushing. But let's say you solve the power problem. You have reliable, abundant energy on Mars. Now you face the return trip, which might be the most impossible part of all. To launch from Mars back to Earth requires a rocket. That rocket needs fuel. You have two options. Bring the fuel from Earth, which means landing tens of metric tons of explosive propellant on Mars and keeping it stable for years, or produce the fuel on Mars using in situ resource utilization, or ISRU. The ISRU concept sounds elegant. Use Martian atmospheric CO2 and water extracted from underground ice to produce methane and oxygen through the Sabatier reaction. It's chemistry we understand. It's been demonstrated in labs. But doing it on Mars, at scale, with limited equipment and power, in a hostile environment, that's never been attempted. Dr. Robert Zubrin estimates you'd need about 100 metric tons of methane and oxygen to launch from Mars. Producing that would take years of continuous chemical processing using imported equipment that has to work perfectly the first time because there are no second chances. What if the ISRU system fails? What if you can't find accessible water ice? What if the equipment breaks down? You're stuck on Mars permanently. The return vehicle sits there, useless, a monument to overconfidence. And the crew has to accept that they're going to die on Mars, slowly running out of supplies, waiting for systems to fail one by one. That scenario isn't pessimism. It's realism based on the complexity of what's being attempted. In 2021, SpaceX began testing the Raptor engine designed to run on methane produced on Mars. The engine works brilliantly on Earth, but Earth has mechanics, spare parts, controlled conditions, and immediate support. Mars has none of that. Every seal, every valve, every sensor in that engine has to function perfectly after sitting dormant on Mars for 18 months, exposed to temperature extremes, dust infiltration, and radiation. The probability of everything working exactly as needed approaches zero. Here's what really blows my mind. We're talking about betting human lives on technologies that have never been tested in the actual environment where they'll be used. You can simulate Mars on Earth, but you cannot replicate it. The dust is different. The radiation environment is different. The temperature extremes are different. Equipment that works in simulation fails in reality. We've seen this repeatedly with Mars landers and rovers. They encounter unexpected problems that couldn't be predicted because Mars is always more hostile than our simulations suggest. Dr. Carol Stoker from NASA's Ames Research Center has been designing Mars missions for 30 years. She's become progressively more pessimistic about human missions. In a 2019 interview, she said something that stuck with me. Every time we learn more about Mars, it gets harder, not easier. We keep discovering new problems faster than we solve old ones. At some point, you have to ask if we're approaching an asymptote, a limit beyond which human missions aren't just difficult, but impossible. The mass constraints, the energy requirements, the need for perfect reliability in systems that will operate for years without maintenance, the biological degradation of the crew, the psychological pressure, all of it combining into a challenge that might simply be beyond our capabilities, not just now, but perhaps forever. Because the problems aren't technological. They're fundamental. They're physics. You can't innovate your way around the rocket equation. You can't engineer yourself past the speed of light limitation on travel times. You can't wish away the radiation or the dust or the cold or the isolation. Think about this. The International Space Station costs about $150 billion to build and requires constant resupply missions to keep 3 to 6 people alive just 250 miles above Earth's surface, where rescue is hours away. A Mars base would cost vastly more, require vastly more complex logistics, and support people millions of miles from help. The economic absurdity of it becomes apparent when you actually calculate the cost per person per day. We're talking about potentially trillions of dollars to keep a handful of people alive on a planet that's trying to kill them, achieving little scientific value that couldn't be accomplished with robots for a tiny fraction of the cost. Let me show you something that puts all of this in perspective. Distance. We talk about Mars like it's our neighbor, Earth's sister planet, a short hop across the solar system. The reality is so much more isolating that it defies human intuition. Mars at its closest approach to Earth is about 56 million kilometers away. At its farthest, it's 401 million kilometers away. The distance changes constantly as both planets orbit the Sun at different speeds. This means that a Mars mission isn't just a trip, it's a navigational nightmare of constantly updating trajectories and narrow launch windows. A launch window to Mars opens only once every 26 months when the orbital mechanics align properly. Miss that window, and you wait over 2 years for the next one. But here's the truly disturbing part. Even during the optimal launch window, the journey takes about 7 to 9 months one way using current propulsion technology. That's 7 to 9 months of microgravity, radiation exposure, isolation, and complete dependence on your spacecraft systems. If anything critical fails during that time, there's no pulling over, no calling for help, no going back. You're committed to the trajectory. Think of it like this. Imagine getting on a boat to cross an ocean, but the moment you leave shore, you cannot turn around. The currents won't allow it. You can only go forward, taking 9 months to reach the other side. And if your boat springs a leak halfway across, you bail water and hope you make it, because there is no rescue. That's a Mars transit. Except instead of water, you're surrounded by vacuum and radiation, and instead of drowning, you suffocate or die of dehydration or starvation, or a dozen other ways. During Apollo 13, when an oxygen tank exploded, the crew was about 200,000 miles from Earth. Mission Control had hours to calculate solutions, and the spacecraft could course correct to get back to Earth in about 3 days. The world watched in collective anxiety for those 3 days, praying for their safe return. Now imagine the same scenario happening halfway to Mars. The crew is 4.5 months from Earth and 4.5 months from Mars. There is no quick return. There is no rescue mission. Mission Control can communicate solutions, but with a time delay that grows up to 22 minutes one way. A conversation takes 44 minutes round trip. Houston, we have a problem, would be followed by 44 minutes of silence before any response. The crew would need to solve life-threatening emergencies, essentially alone while the world watches helplessly from 200 million miles away. Dr. Louis Friedman, co-founder of the Planetary Society, wrote something in 2015 that was controversial, but increasingly seems prophetic. Humans will never reach Mars. The distance, the time, the radiation, and the cost make human Mars missions an impossible dream that we should stop pursuing. He wasn't being pessimistic. He was being mathematical. The energy required to move a human-rated spacecraft with all necessary supplies across interplanetary distances exceeds our capacity to generate and focus that energy efficiently. Let me give you a thought experiment. Imagine you wanted to drive to Mars. If you could somehow build a road through space and drive at highway speeds, 100 kilometers per hour non-stop, it would take you 64 years to reach Mars at its closest approach. 64 years of constant driving. That's how far away it actually is. We can go faster with rockets, obviously, but the principle remains. Mars is not a distant mountain you can see across a valley. It's an almost incomprehensibly remote location, separated from us by a void so vast that light itself takes between 3 and 22 minutes to cross it. And here's what really keeps me up at night. Even if everything goes perfectly, even if every system works, even if the crew stays healthy and sane, they're still facing about 2.5 to 3 years away from Earth. The International Space Station is continuously inhabited, but it's in low Earth orbit. Earth fills the windows. Astronauts can see home. They can watch weather patterns, see lights from cities, witness sunrises over continents. It maintains a psychological connection to home. On Mars, Earth is a pale blue dot, barely distinguishable from stars. The psychological impact of that isolation, that sense of absolute remoteness, has never been experienced by humans before. In 1972, the Apollo 17 astronauts took the famous blue marble photograph from 29,000 kilometers away. Earth filled the frame, a beautiful sphere of clouds and oceans. From Mars, Earth would appear as a bright star, no different to the naked eye than Venus appears from Earth. That's it. Everything you've ever known, everyone you've ever loved, all of human history and civilization, reduced to a point of light among thousands of others. The astronomer Carl Sagan called Earth a mote of dust suspended in a sunbeam when describing the pale blue dot image from 6 billion kilometers away. From Mars, that mote is all you have left of home. What if I told you that the Apollo astronauts, who only went to the moon, reported profound psychological effects from seeing Earth at a distance. The overview effect, they called it, and cognitive shift in awareness, a sense of Earth's fragility, a dissolving of national boundaries and human conflicts in the face of cosmic perspective. Some astronauts reported depression after returning. Some turned to religion. Some became environmental activists. Some struggled to readjust to normal life because normal life seemed trivial after touching another world. Now multiply that effect by 1,000. Multiply the distance by 1,000, the isolation by 1,000, the duration by 10. What happens to the human psyche under that pressure? Dr. Nick Kanas, a psychiatrist who studied astronaut psychology for decades, published research showing that psychological issues increase with mission duration and crew isolation. Cognitive decline, depression, interpersonal conflict all worsen over time. The longest his studies covered was 6 months on the ISS. A Mars mission would be 3 to 5 times longer. We're extrapolating far beyond our data, and the extrapolation suggests that psychological collapse becomes not a possibility, but a probability. Think about living in a small house with 5 other people for 3 years, unable to leave except to step into a hostile environment, wearing a cumbersome suit, knowing that any mistake could kill everyone, watching Earth shrink to a point of light, receiving messages from home with ever-increasing delays as the distance grows, dealing with constant equipment failures, managing scarce resources, all while your body deteriorates from radiation and microgravity. How long before someone snaps? How long before the stress fractures the social cohesion necessary for survival? And what happens when they do? There's no privacy on a spacecraft or Mars habitat. No personal space. No escape from each other. Every irritating habit, every personality clash, magnified by proximity and stress. On Earth, if you're having a conflict with a coworker, you go home at night. You have separate lives. On a Mars mission, your coworker sleeps 6 feet away from you. You eat together, work together, exercise in the same tiny space, use the same bathroom, breathe the same recycled air every single day for years. The potential for psychological breakdown isn't a flaw in mission planning. It's an inevitability of human nature. The Soviet Salyut and Mir space stations had multiple instances of crew conflict serious enough to affect mission operations. One crew stopped speaking to each other. Another broke off communications with ground control due to interpersonal stress. These were professional astronauts, highly trained, psychologically screened, on missions lasting months. The selection process for Mars would be even more rigorous, but you cannot screen out human nature. You cannot train away the fundamental need for personal space, privacy, and autonomy. You cannot prepare someone for the psychological reality of knowing they might never see Earth again. Dr. Peter Subfeld from the University of British Columbia studied the journals and communications of Antarctic researchers, submariners, and astronauts to understand the psychology of isolation. His findings are disturbing. Around the halfway point of isolated missions, a phenomenon called the third quarter effect occurs. Motivation plummets, depression spikes. The initial excitement has worn off, but the end is still too far away to provide hope. People become irritable, withdrawn, sometimes irrational. In Antarctica, this is manageable because rescue is theoretically possible. In a submarine, you can surface. On Mars, there is no relief. The third quarter effect would hit when you're still a year away from potential return, with your body degraded, your supplies dwindling, and your psychological reserves exhausted. Here's something that will blow your mind. Communication delays make Earth-based psychological support almost useless. When the time delay reaches 20 minutes one way, you can't have a real conversation. You can't talk through a crisis in real time. If an astronaut is having a psychological breakdown, mission control can send advice, but 40 minutes will pass before the astronaut receives it. By then, the crisis might have escalated beyond words. Someone might have hurt themselves or others. Equipment might be damaged. The mission might be over. And mission control could only watch the disaster unfold via time-delayed transmissions, powerless to intervene. Think about this scenario. An astronaut develops severe depression on Mars. On Earth, treatment involves therapy, medication adjustments, support networks, sometimes hospitalization if there's risk of self-harm. On Mars, you have a limited supply of psychiatric medications that might not work or might have side effects you can't manage. You have no therapist, just recorded messages from Earth that arrive 40 minutes after you ask for help. You have no support network beyond the 5 people you're trapped with, who are also struggling with their own psychological issues. You have no hospital, no psychiatric ward, nowhere to ensure the safety of someone in crisis. What do? Sedate them? Restrain them? Watch them constantly? Each solution creates new problems in an already stressed crew dynamic. In 2011, the Mars 500 simulation experienced what they called a psychological incident that was never fully disclosed. Something happened that was serious enough to nearly end the experiment early. The crew recovered, the simulation continued, but the incident revealed that even with the knowledge that they were on Earth and could leave, psychological pressure can overwhelm trained individuals. On actual Mars, that pressure would be incomparably worse. The isolation from Earth goes beyond just distance. It's temporal isolation too. News from Earth arrives with a delay. You watch events unfold that have already concluded by the time you learn about them. If a family member becomes ill, you find out after they might already be dead. If there's a disaster on Earth, you learn about it when it's already history. You exist in a timeline offset from the rest of humanity, always living in Earth's past, unable to participate in the present. The psychological alienation of that temporal displacement has never been studied because it's never been experienced. What if someone on the crew wants to come home but can't? Not because of physical constraints, but because the orbital mechanics won't allow it for another year? On the ISS, if an astronaut has a family emergency or develops a condition that requires return, they can be back on Earth within hours. On Mars, you're locked into the orbital transfer windows. If your father is dying and you want to say goodbye, you might have to wait 18 months for the planets to align properly for a return trajectory. You'd miss the funeral by years. You'd return to a world that has moved on without you. The psychological toll of that powerlessness, that forced abandonment of earthly connections, could break even the most resilient person. Dr. Jack Stuster, who wrote the definitive book on the psychology of isolated and confined environments, interviewed dozens of astronauts, Antarctic researchers, and submariners. One theme emerged repeatedly: the importance of knowing you can leave. Even if you don't actually leave, even if you complete your mission, the knowledge that extraction is possible provides psychological comfort. Mars removes that entirely. You cannot leave. There is no emergency extraction. There is no quit option. You're committed absolutely, and that absolute commitment creates a unique form of psychological pressure that humans have never experienced before. The communication itself becomes a source of pain. Families on Earth age in real time while you watch via delayed video messages. You see your children grow up in jumps, missing the daily moments that make up a childhood. Your parents get older, frailer. Your spouse might develop feelings for someone else. Life continues without you, and you're reduced to a spectator receiving reports from a world you no longer belong to. Some psychologists have suggested that this delayed connection might be worse than no connection at all. A form of torture where you're constantly reminded of what you've lost without being able to participate in it. And here's the ultimate psychological nightmare. What if you succeed? What if you make it to Mars, spend 18 months there, and successfully return to Earth? You've been gone for 3 years. You're permanently physically damaged from radiation and microgravity. You've experienced trauma that no one else on Earth can relate to. You've been to another planet, seen Earth as a distant star, experienced isolation beyond human comprehension. How do you reintegrate into normal society? How do you relate to people whose biggest concern is traffic or work deadlines when you've lived every day knowing a single mistake meant death? Apollo astronauts struggled with this. Buzz Aldrin battled depression and alcoholism after returning from the moon. Many divorced. Some withdrew from public life. And they were only gone for a week or two. Still within Earth's gravitational embrace. Still able to see home out the window. They were treated as heroes upon return, given parades and honors. Mars astronauts would return to a world that had moved on, to a media cycle that had forgotten them, to physical disabilities and psychological scars, to medical problems that would plague them for life. They'd be case studies, not heroes. Patients, not pioneers. Think about the fundamental absurdity. We're considering sending humans on a mission so dangerous, so isolating, so physically and psychologically destructive, that success means returning damaged for life, and failure means dying slowly while the world watches helplessly from millions of miles away. What kind of scientific advancement justifies that cost? What knowledge is worth the suffering? What achievement is worth the trauma? These aren't rhetorical questions. They're ethical imperatives we're ignoring in our rush to plant flags on another world. Now let's talk about something that combines all of these problems into one nightmare scenario: interplanetary travel times and the speed of light limitation. This isn't just about Mars being far away. This is about the fundamental structure of space-time, making rapid interplanetary travel physically impossible with any technology we can envision or theoretically construct. The speed of light, 299,792 kilometers per second, isn't just a speed limit for light. It's the maximum speed at which information, energy, or matter can travel through the universe according to Einstein's special relativity. Nothing with mass can reach the speed of light because doing so would require infinite energy. Our fastest spacecraft, the Parker Solar Probe, reaches about 192 kilometers per second at perihelion, about 0.064% the speed of light. At that speed, reaching Mars at its closest approach would still take about 3 days if you could maintain that velocity and brake on arrival, which you can't. Realistically, with current propulsion, 7 to 9 months. But let's dream big. Let's imagine we developed fusion propulsion, which is theoretically possible, but decades away from practical implementation. Fusion rockets could potentially reach 5% the speed of light, given enough time to accelerate. At 5% light speed, you could reach Mars in hours instead of months. Problem solved, right? Except here's what happens when you travel through space at relativistic speeds. Every particle of dust, every stray hydrogen atom, becomes a bullet of devastating kinetic energy. Dr. William Edelstein from Johns Hopkins University calculated that a spacecraft traveling at just 10% the speed of light through the interstellar medium would be bombarded by cosmic rays and interstellar particles with enough energy to kill the crew from radiation exposure within minutes. The spacecraft would need shielding meters thick to protect against this, making the vehicle too massive to accelerate to those speeds in the first place. It's another catch-22. You need to go fast to make the journey tolerable, but going fast makes the journey lethal unless you add shielding that makes going fast impossible. Even if you solve the shielding problem, the energy requirements are staggering beyond comprehension. To accelerate a 1,000 metric ton spacecraft to 5% light speed requires approximately 1.1 times YP joules of energy. That's 1.1 exajoules. To put that in perspective, the entire world's energy consumption in 2020 was about 580 exajoules for the whole year. You'd need about 0.2% of global yearly energy production to launch a single mission, and that's just to accelerate. You need the same amount of energy again to decelerate at Mars, or you fly right past it at 15,000 kilometers per second. Doubling the energy requirement means you'd need 0.4% of global energy production for one Mars mission. Think of it like this. Imagine you wanted to throw a baseball to the moon. The energy required is calculable, and it's enormous. Now imagine you wanted to throw a house to the moon. The energy required scales with mass. Now imagine you wanted to throw that house to the moon in 5 minutes instead of 3 days. The energy required scales with velocity squared. Space travel faces both constraints. Massive payloads that need to travel at high speeds. The energy requirements become absurd very quickly, and we're already pushing against fundamental limits with chemical rockets. Some propose using nuclear pulse propulsion, the Orion concept, where you detonate nuclear bombs behind a spacecraft to push it forward. The concept was developed in the 1950s and abandoned for numerous reasons, including international treaties, banning nuclear weapons in space, the impossibility of surviving the acceleration, and the minor detail that you'd be detonating hundreds of nuclear weapons, each one potentially failing and destroying your spacecraft. It's theoretically possible, but practically insane. What about ion drives, which provide continuous low thrust over long periods? They work brilliantly for unmanned probes. The Dawn spacecraft used ion propulsion to visit Vesta and Ceres. But ion drives produce thrust measured in fractions of a newton. The acceleration is so gentle that a human crew would die of old age before reaching significant velocity. You'd need months just to accelerate to coasting speed, months to decelerate, and the mission duration extends beyond the physical endurance of humans. The radiation exposure alone during a years-long ion drive Mars mission would be lethal multiple times over. Here's what will blow your mind. Even if we developed some magical propulsion system that could accelerate us to high velocities without killing us and decelerate safely at our destination, we still face the tyranny of distance in terms of communication. The Mars rovers operate with delays of 4 to 24 minutes one way. Every command sent from Earth is executed long after the situation might have changed. Rovers have gotten stuck, malfunctioned, and failed because of this delay. Now imagine trying to coordinate a complex human mission with that lag. Every conversation is disjointed. Every emergency requires autonomous decision-making by the crew, because waiting for advice from Earth means waiting until the crisis has resolved or escalated beyond control. Dr. Robert Forward, a physicist who spent his career working on advanced propulsion concepts, concluded near the end of his life that the distances in space might simply be too vast for human exploration beyond the moon, not because we lack imagination or technology, but because the laws of physics genuinely prohibit it. The speed of light limit isn't a technological barrier we'll overcome with better engineering. It's a fundamental property of space-time itself. And traveling at any significant fraction of light speed introduces relativistic effects, energy requirements, and dangers that might be genuinely insurmountable. Think about the Voyager probes. Launched in 1977, they've been traveling for over 45 years at about 17 kilometers per second. They're about 23 billion kilometers from Earth now, in interstellar space, the farthest human-made objects from home. At their current speed, they take about 70,000 years to reach the nearest star system, Proxima Centauri, 4.24 light-years away. 70,000 years. That's not a mission. That's a geological timescale. That's the entire span of human civilization. And Proxima Centauri is our closest stellar neighbor. Some people fantasize about generation ships, massive vessels that would take centuries to reach other stars, with crews living and dying aboard, their descendants eventually arriving at the destination. Setting aside the engineering impossibility of building such a vessel, the biological impossibility of maintaining a healthy gene pool with limited population, and the psychological impossibility of condemning generations to life in a can, consider this. Who gets to decide to send people on such a mission? What right does one generation have to imprison all subsequent generations in a spacecraft? It's essentially creating a small civilization of slaves, born without choice, into a mission their great-great-grandparents started. The ethics are monstrous. But even Mars doesn't require generation ships. It only requires 7 to 9 months one way. And even that relatively short journey faces insurmountable barriers. If we can't reliably send humans to Mars and back, if the closest planet besides Venus is beyond our biological capabilities to reach and survive on, what hope do we have for anything farther? Jupiter is 5 times farther than Mars. Saturn is 10 times farther. The outer solar system might as well be in another galaxy for all the practical possibility of human exploration. Here's the reality nobody wants to face. The solar system is mind-bogglingly vast. The galaxy is incomprehensibly larger, and the universe is so big that words fail to capture its scale. And humans are fragile biological machines optimized for one specific environment on one specific planet, orbiting one specific star. We're not cosmic explorers. We're terrestrial organisms with the cognitive ability to imagine ourselves elsewhere. But imagination doesn't change physics. Wanting to explore space doesn't make it possible. Dreaming of Mars colonies doesn't make them viable. And pretending these are engineering challenges rather than fundamental physical constraints doesn't make them solvable. Let's shift to something that makes all of this even more depressing: economics. Because even if we could solve every technical and biological problem I've described, the sheer cost of human space exploration makes it an impossibility at civilizational scale. The Apollo program cost about $280 billion in today's dollars. That was for 9 missions to the moon, 6 of which landed, keeping humans there for at most 3 days at a time. We went to a destination 384,000 kilometers away, stayed briefly, and came home. The entire program employed 400,000 people at its peak and consumed about 4% of the federal budget. A human Mars mission would cost conservatively 10 to 20 times more. NASA's own estimates for a Mars mission range from $500 billion to over $1 trillion, depending on the architecture. SpaceX's Elon Musk claims he can do it cheaper, maybe $100 billion to $200 billion. Let's be generous and accept his optimistic estimate. That's still $100 billion minimum for the first mission. Not for a colony, not for a permanent presence. For one mission with maybe a handful of astronauts spending 18 months on Mars before returning. Think of what else $100 billion could accomplish. That money could provide clean water to every human on Earth who lacks it, estimated at about 2 billion people, for decades. It could fund malaria eradication, estimated to cost about $90 billion total. It could address climate change mitigation, build renewable energy infrastructure, improve education globally, cure diseases that affect millions. The opportunity cost of human Mars missions is measured in earthly suffering we could alleviate, but choose not to in favor of sending a handful of people to die slowly on a dead planet. Dr. Robert Park, a physicist who spent decades at the American Physical Society, argued repeatedly that human spaceflight is a waste of resources that could be better spent on robotic exploration and earthly problems. He pointed out that every scientific objective proposed for human Mars missions could be accomplished by robots for a tiny fraction of the cost with zero risk to human life. The Curiosity rover cost about $2.5 billion and has been exploring Mars for over a decade. You could send 40 rovers for the cost of one human mission, covering vastly more territory, taking more samples, making more discoveries. The counter-argument is always inspiration, intangible benefits, advancing human knowledge and capabilities. But inspiration doesn't cure diseases. Inspiration doesn't feed hungry children. Inspiration doesn't stop climate change. And the knowledge gained from sending humans to Mars, rather than robots, is primarily knowledge about how humans suffer and die in space, which we could gather more ethically by not sending them in the first place. Here's something that will blow your mind. The International Space Station. Humanity's greatest space achievement has cost over $150 billion to build and operate. It orbits 250 miles above Earth's surface. That's about the driving distance from New York to Washington, D.C. for $150 billion. We've kept 3 to 6 people alive in an orbiting laboratory that's relatively easily accessible and resupplied. Now imagine the cost of keeping people alive on Mars, millions of miles away, requiring years-long supply missions with no possibility of quick rescue or resupply. The costs scale exponentially with distance and risk. SpaceX's Starship program aims to reduce costs through reusability. The concept is sound. If you can reuse rockets instead of discarding them, costs come down dramatically. But even with perfect reusability, you still face the tyranny of the rocket equation, the need for multiple launches, the need for orbital refueling, the need for systems that work perfectly in environments they've never been tested in. And reusability requires returning the vehicle to Earth, which means bringing it back from Mars, which means fuel produced on Mars, which means I says RU systems that work perfectly, which brings us back to all the technical impossibilities we've discussed. Think about this. When the Apollo program ended in 1972, it wasn't because we'd accomplished everything we wanted. It was because the American public lost interest and Congress cut funding. The missions became routine. The excitement faded. The cost became unjustifiable. The same would happen with Mars missions, except faster and more dramatically, because the missions would be longer, more expensive, and more dangerous. The first mission might capture global attention. The second would generate less interest. By the third, it would be background news. And when the first crew dies, when the inevitable disaster happens, public support would evaporate instantly. In 2003, the Space Shuttle Columbia disintegrated during re-entry, killing 7 astronauts. The disaster grounded the shuttle fleet for 2.5 years and ultimately contributed to the program's cancellation. The shuttle was flying to low Earth orbit, a relatively benign environment. Imagine the public reaction when a Mars crew dies slowly over months while the world watches via delayed transmissions. Imagine the political fallout. Imagine the lawsuits, the investigations, the congressional hearings. Human space exploration would end instantly, and the taboo against it might last generations. Dr. George Mueller, who managed the Apollo program, said in a later interview that they succeeded partly through luck. Critical systems worked when they might have failed. Decisions made without complete information turned out correct. The crews avoided disasters that could easily have occurred. He estimated that if they'd flown Apollo 100 times, they would have lost perhaps 10 or 20 crews. That's a 10 to 20% failure rate for missions to the Moon. Mars missions are orders of magnitude more complex and dangerous. The failure rate would be higher, perhaps much higher. Insurance companies won't cover human Mars missions. The risk is incalculable and essentially certain. No rational insurance model would accept a 10% or higher chance of total loss. This means governments or private entities would self-insure, accepting the risk of losing billions of dollars along with human lives. When the first mission fails, the financial loss alone might bankrupt the space agency or company responsible. SpaceX, for all its success, has a market valuation around $100 billion. A single catastrophic Mars mission failure could destroy the company financially. What if I told you that every dollar spent on human spaceflight is essentially a subsidy for solving problems we've chosen to have? We've chosen to leave Earth despite our biological incompatibility with space. We've chosen to invest resources in overcoming that incompatibility instead of accepting it. We've chosen to prioritize flags and footprints over practical benefits. And we've justified it with vague promises of inspiring future generations and becoming a multi-planetary species, neither of which is measurable or achievable given the constraints we face. The Mars Society, founded by Robert Zubrin, has been advocating for human Mars missions for decades. Their membership peaked at about 10,000 people worldwide. That's 0.001% of global population, actively interested in Mars exploration, enough to join an advocacy group. The vast majority of humanity doesn't care about Mars. They care about their immediate lives, their families, their communities, their planet. Spending trillions on Mars missions benefits the tiny fraction who dream of space, while ignoring the billions who need help here on Earth. Think about global priorities. Climate change threatens hundreds of millions with displacement, famine, and conflict. Biodiversity loss is occurring at rates not seen since mass extinction events. Poverty, disease, lack of clean water, and sanitation affect billions. Educational inequality perpetuates cycles of disadvantage. And we're seriously discussing spending $1 trillion to send a handful of people to a dead planet where they'll accomplish little of scientific value before dying prematurely from radiation-induced cancers. The moral calculus doesn't just fail. It's obscene. Some argue that technological spin-offs from space programs justify the investment. Velcro, freeze-dried food, satellite technology, all supposedly products of space exploration. This is mostly myth. Most space program technologies were adapted from existing innovations, not created de novo. And the technologies that were developed for space would likely have been developed anyway for other applications given equivalent investment. You don't need to go to Mars to invent better water filtration systems. You can develop them specifically for water filtration and get better results for less money. The economic reality is brutal. Human spaceflight beyond low Earth orbit cannot be justified by any rational cost-benefit analysis. It's a civilizational vanity project, a species-level expression of ego and denial, a refusal to accept that we're bound to Earth, not by lack of will or imagination, but by the fundamental physics and biology of existence. And the longer we pursue it, the more resources we waste that could be improving life for the billions of humans already struggling on the planet we evolved to inhabit. Now let's talk about something that pulls all of this together into one inescapable conclusion: evolutionary mismatch. We are not just adapted to Earth. We are Earth. Every cell in your body, every physiological system, every cognitive process evolved under specific conditions. 1 G of gravity, a 24-hour day, a protective magnetic field, abundant liquid water, breathable atmosphere with 21% oxygen, surface pressure of 101.3 kilopascals, and temperatures within a narrow range. These aren't just nice-to-haves. They're the fundamental conditions under which life on Earth evolved for billions of years. Dr. Sean Carroll, an evolutionary biologist at the University of Wisconsin, points out that evolution doesn't create generalists who can survive anywhere. It creates specialists optimized for specific niches. A polar bear is magnificently adapted to the Arctic, but would die quickly in a desert. A camel thrives in deserts, but couldn't survive the Arctic. These aren't weaknesses. They're the inevitable result of evolutionary optimization. You can't be perfectly adapted to every environment. You adapt to your environment, and that adaptation makes you dependent on it. Humans evolved in East Africa about 300,000 years ago. Our bodies, our brains, our physiologies are fine-tuned for that ancestral environment, modified slightly as we spread across Earth, but remaining fundamentally terrestrial, gravity-dependent, atmosphere-breathing organisms. We did not evolve with any exposure to space. There was no evolutionary pressure to develop radiation resistance, microgravity tolerance, or the ability to survive without atmospheric pressure. These capabilities don't exist in our genome because they were never needed. Think of it like this. A fish evolved to breathe water through gills. No amount of training will allow that fish to breathe air. Its respiratory system is fundamentally structured for extracting oxygen from water. To breathe air, it would need to evolve lungs, a process that took millions of years and countless intermediate forms. We're like fish trying to live on land without lungs. We can build machines that help us temporarily, but we cannot fundamentally change what we are. In 2020, Dr. Christopher Mason from Weill Cornell published a comprehensive study on the future of human space exploration. His conclusion was remarkable. To truly colonize space, humans would need to be genetically engineered, significantly modified from what we currently are. We'd need radiation-resistant DNA, repair mechanisms borrowed from extremophile bacteria. We'd need bone density independent of gravitational loading. We'd need cardiovascular systems that function in multiple gravity regimes. We'd need to be, essentially, a different species. Not humans anymore, but post-humans adapted for space. And even if we were willing to do that, even if we could ethically justify genetically engineering space-adapted humans, the timescale would be enormous. Evolution works through generations. Even with genetic engineering shortcuts, you'd need multiple generations of space-adapted humans, each slightly better adapted than the last, gradually diverging from Earth-based humanity. You'd create a speciation event, splitting Homo sapiens into Earth humans and space humans. They'd be unable to interbreed eventually, separated not just by distance, but by biology. Here's what really blows my mind. This isn't science fiction speculation. This is basic evolutionary biology applied to space colonization. If you want humans in space long term, they won't be humans as we understand the term. They'll be something else, something we created, something that might look at us the way we look at our primate ancestors, related but separate. And that raises profound questions. Do space-adapted post-humans have human rights? Are they our children or our creations? Do they owe us anything? Do we owe them anything? Dr. Paul Root-Wolpe, a bioethicist at Emory University, argues that creating space-adapted humans would be one of the most profound ethical decisions in human history, comparable to creating artificial general intelligence. You're not just modifying a human. You're creating a new branch on the evolutionary tree, beings that will exist for potentially millions of years, all stemming from decisions we make in this century. The responsibility is crushing, and we're nowhere near ready for that decision. But let's bring this back to the present. We're not talking about genetically engineered post-humans. We're talking about sending current humans, with our current biology, to Mars. And the evidence is overwhelming that we're not capable of surviving there long-term. Not with any technology we have or can envision. Not with any amount of training or preparation. Our bodies will fail. Our minds will break. Our species is earthbound, not by choice, but by the fundamental constraints of what we are. Think about how plants grow on Earth. They orient towards sunlight through gravitropism and phototropism. Roots grow down, stems grow up, all guided by gravity and light. In space, plants become confused. They grow in random directions. Their internal organization becomes chaotic. These are simple organisms, yet they can't develop properly without gravitational cues. Now think about human embryonic development, vastly more complex, requiring precise spatial organization of developing tissues. The probability of normal human development in microgravity or partial gravity approaches zero. No mammal has ever successfully reproduced in space across a complete life cycle. We've tried with rodents, and the results are disturbing. Pregnancies fail at higher rates. Offspring show developmental abnormalities. Maternal stress hormones remain elevated. And these are short-duration experiments. A successful human Mars colony would require multiple generations born and raised on Mars, each one an experiment in whether human reproduction is even possible outside Earth's gravity. What if I told you that every proposal for Mars colonization implicitly assumes we can overcome our evolutionary heritage through willpower and technology? But evolution doesn't work that way. You can't engineer around 4 billion years of adaptation in a few decades of research. The changes required to make humans space compatible would take millions of years of natural selection or radical genetic engineering. that we're nowhere close to safely implementing. Dr. Nathaniel Comfort, a historian of biology at Johns Hopkins, points out that the history of human genetic engineering is a history of unexpected consequences. We think we understand how genes work, then discover epigenetic factors, then gene-environment interactions, then regulatory networks of stunning complexity. Every layer of understanding reveals how much we don't know. The idea that we could safely engineer humans for space without creating catastrophic unintended consequences is hubristic in the extreme. And even if we could, even if we successfully created space-adapted humans, we'd face the question, what was the point? If humans can't go to space, so we create post-humans who can, have we really expanded humanity into space? Or have we just created a new species and sent them into exile? The philosophical question matters. If the goal is human space exploration, and achieving it requires creating beings that aren't human, then we've failed by definition. The evolutionary reality is this: we're trapped on Earth by billions of years of adaptation to Earth. Every system in our bodies assumes Earth conditions. Every physiological process depends on gravitational, atmospheric, and magnetic parameters that exist only on Earth. We aren't imprisoned by technology or economics or politics. We're imprisoned by biology, by evolution, by the fundamental nature of what we are. And no amount of engineering can change that without changing what we means. Think about this. Every organism on Earth is bound to specific conditions. Alpine plants die at sea level. Deep-sea organisms explode when brought to the surface. Desert animals die in rainforests. This isn't weakness. This is specificity. This is optimization, and humans are no different. We're optimized for Earth. We die elsewhere, not eventually, not from old age, but quickly, painfully, from multiple simultaneous system failures caused by environmental mismatch. We are Earth life, and Earth life doesn't work on Mars. So where does this leave us? We've talked about radiation that tears apart DNA. We've discussed bone loss that cripples astronauts. We've explored immune system collapse, microbial dysbiosis, psychological breakdown, communication delays, energy requirements, economic impossibilities, and evolutionary constraints. Every angle of analysis reaches the same conclusion. Humans leaving Earth for extended periods is somewhere between extremely difficult and fundamentally impossible. Not difficult like climbing Everest is difficult. Impossible like a fish climbing Everest without water. But here's where this gets personal. Here's where this affects you, watching this video, living your life on Earth. Because the fantasy of leaving Earth, the dream of becoming a multiplanetary species, it's not just wrong, it's actively harmful. It's a distraction from the reality we need to face. Earth is the only home we will ever have, and we're destroying it. Every dollar spent on Mars colonization is a dollar not spent on climate change mitigation. Every brilliant engineer working on spacecraft design is someone not working on renewable energy, carbon capture, ocean cleanup, or ecosystem restoration. Every politician championing space exploration is someone not championing the urgent work of healing our planet. The Mars fantasy allows us to imagine an escape route from our self-created problems, which paradoxically makes us less motivated to solve them. Think of it like someone with a serious health condition who refuses treatment because they're planning to upload their consciousness to a computer someday. The upload isn't possible. The technology doesn't exist and might be impossible, but the fantasy of it allows them to avoid the difficult, unglamorous work of actual treatment. That's us with Mars. We've given ourselves a planetary-scale health crisis through climate change, pollution, habitat destruction, and resource depletion. And instead of treating it, we fantasize about abandoning the patient and moving to a new body that doesn't exist and can't exist. Dr. Kate Marvel, a climate scientist at NASA Goddard, put it perfectly. There is no planet B. The same forces that have led to environmental crisis on Earth would follow us to Mars. We don't need a new planet. We need to be better stewards of this one. And she's right. The problems we face on Earth, overpopulation, resource scarcity, environmental degradation, none of these are solved by going to Mars. They're all vastly worse on Mars, where resources are even scarcer, the environment is even more hostile, and the logistics of survival are infinitely more complex. Imagine we achieved the impossible. Imagine we somehow got a colony of 1,000 people established on Mars, surviving against all the odds we've discussed. Earth's population is 8 billion. Mars houses 0.000125% of humanity. Meanwhile, Earth continues heating. Ocean levels rise. Species go extinct. Ecosystems collapse. Does that colony of 1,000 make any difference? Are they humanity's backup? Or are they a rounding error, a symbolic gesture that accomplished nothing while the real crisis unfolded back home? The hard truth is this: the only planet we can terraform is Earth. The only atmosphere we can modify to be breathable is Earth's atmosphere. The only ecosystem we can restore is Earth's ecosystem. We have all the tools, knowledge, and technology to make Earth a paradise. We're choosing not to use them while fantasizing about making Mars mediocre. The priorities are inverted. We're ignoring the garden to dream about the wasteland. Here's what will blow your mind. Making Earth sustainable would be thousands of times easier and cheaper than colonizing Mars. Transforming our energy infrastructure to renewables, estimated cost around $70 trillion globally over 30 years. Creating a Mars colony capable of housing even 10,000 people, easily over $10 trillion, probably much more. We could solve climate change, restore ecosystems, end poverty, provide clean water to everyone, and build sustainable food systems for less than it would cost to establish a minimal Mars presence that serves no practical purpose. Dr. James Lovelock, who developed the Gaia hypothesis, argued that Earth is a self-regulating system that has maintained conditions suitable for life for billions of years. Mars was once more Earth-like, but lost its atmosphere, water, and magnetic field. It's a dead planet, and we lack the technology to resurrect it. Even if we could, it would take thousands of years. Earth, by contrast, can be healed in decades if we commit to it. We're choosing to fantasize about the impossible while ignoring the achievable. Think about your own life. Where do you want to live? On Earth, with its blue skies, breathable air, abundant water, diverse life, natural beauty, and family and friends? Or on Mars, in a cramped habitat, breathing recycled air, drinking recycled urine, eating synthetic food, never feeling wind on your face or rain on your skin, slowly dying from radiation while watching Earth as a distant star? The choice isn't just obvious. It's trivial. Earth is paradise. Mars is hell. And we're considering condemning people to hell while paradise burns. The psychological shift I'm asking you to make is profound. Stop seeing Earth as a starting point and start seeing it as the destination. Stop seeing humanity's future in the stars and start seeing it here, in sustainable equilibrium with the planet that created us. Stop seeing leaving Earth as an achievement and start seeing staying as the choice that reflects wisdom, humility, and love for the only home life has ever known. This doesn't mean abandoning space exploration. Robotic missions are incredible. The James Webb Space Telescope is revealing the universe's deep structure. Mars rovers are teaching us about planetary evolution. Satellites are crucial for communication, weather forecasting, and monitoring Earth's health. Space technology is valuable, but human spaceflight beyond low Earth orbit is a vanity project that diverts resources from urgent earthly needs while pretending to secure humanity's future. What if I told you that accepting our limitations isn't defeat, it's maturity? For centuries, humans dreamed of flying. We achieved it, not by growing wings, but by building machines. But we still can't fly like birds. We're confined to aircraft, dependent on technology, limited by fuel and physics. And that's okay. We don't need to fly like birds to live meaningful lives. Similarly, we don't need to colonize Mars to be a successful species. We need to thrive where we are. Dr. David Grinspoon, an astrobiologist who has spent decades studying planetary habitability, wrote something that changed how I think about this. The universe is not waiting for us to explore it. It doesn't care if we leave Earth or not. But Earth is waiting for us to take care of it. The living planet that created us is asking us to grow up, to take responsibility, to stop treating our home like a disposable resource while fantasizing about a fresh start elsewhere. Think about indigenous cultures that have lived sustainably on Earth for thousands of years. They don't dream of leaving. They dream of maintaining balance, of passing healthy ecosystems to their children, of living in harmony with the land that sustains them. They understand something modern technological civilization has forgotten. You don't need to conquer and expand endlessly. You can find meaning in stewardship, in sustainability, in belonging to a place rather than dominating it. The Mars fantasy is fundamentally a colonialist mindset applied to planets. It's the same thinking that led to the exploitation of Earth's ecosystems and indigenous peoples. The idea that new frontiers exist to be conquered, that expansion is inherently good, that we have the right to take whatever we want, regardless of cost or consequences. It's the worldview that created our current crisis, and applying it to Mars won't solve anything. It will just export our dysfunction to another world. Here's something that keeps me up at night. We're teaching children that humanity's future lies in space. We're filling their heads with images of Mars colonies and interstellar travel, while the planet they actually live on is heating, flooding, and losing biodiversity at catastrophic rates. We're preparing them for a future that can't exist, while failing to prepare them for the future that will exist, one where they'll need to adapt to climate change, resource scarcity, and ecosystem collapse. We're giving them science fiction when we should be giving them ecology, permaculture, and sustainable engineering. The educational system celebrates astronauts as heroes, while environmental activists are often portrayed as naive or radical. We've created a cultural narrative that equates progress with leaving rather than with healing, with escape rather than with responsibility. And that narrative is killing us. Every child who dreams of Mars is a child who might otherwise dream of restoring Earth's rainforests, cleaning the oceans, or developing carbon-negative technologies. We're misdirecting an entire generation's aspirations toward impossibility, while the possible remains undone. Dr. Jane Goodall, who has spent her life studying and protecting Earth's biodiversity, said something profound in a recent interview. The idea that we can destroy Earth and then leave for Mars is the most dangerous fantasy humans have ever constructed. It absolves us of responsibility. It allows us to continue destructive behaviors while imagining a cosmic escape route. But there is no escape. There is only here. There is only now. There is only this planet and what we choose to do with it. Think about the Keeling curve. That graph showing atmospheric CO2 concentrations rising steadily since measurements began in 1958. It's now over 420 parts per million, higher than it's been in millions of years. Every year it climbs. Every year we know we're driving toward catastrophe. And every year billions are spent on space programs while climate action remains inadequate. The priorities are insane. We're polishing the escape pod while the ship sinks, except the escape pod doesn't work and never will. The psychological comfort of the Mars fantasy is understandable. Humans don't handle existential threats well. When faced with overwhelming problems, we either fight, flee, or freeze. Climate change is overwhelming. It's global, it's complex, it's politically contentious, and it requires sustained collective action over decades. That's psychologically exhausting. The Mars fantasy offers flight, a way to avoid the hard work of facing the problem we created. But fleeing to Mars is fleeing to death. The only viable option is to fight for Earth, Here's what really blows my mind. We know how to fix this. Renewable energy technology exists and is becoming cheaper every year. Carbon capture is developing. Reforestation works. Sustainable agriculture is practiced successfully in many regions. Circular economy principles can dramatically reduce resource consumption. The solutions exist. What's missing is collective will, political courage, and a cultural shift away from fantasies of escape toward commitment to repair. And that's where you come in. Yes, you watching this video. You're not powerless. Your choices matter. Every decision to consume less, to use renewable energy, to support politicians who prioritize climate action, to educate others, to challenge the Mars fantasy when you encounter it. All of it contributes to the collective shift we desperately need. You're not just an individual. You're part of a species making a choice about its future. And that choice is, do we commit to Earth, or do we waste our remaining time and resources on impossible dreams of elsewhere? Think about your children, or future children, or any young person you care about. What world are you leaving them? A healing Earth where humanity learned to live sustainably? Or a degraded Earth where we squandered our chance at redemption by pouring resources into Mars colonies that failed, as they were always destined to fail? The choice we make now echoes through generations. And right now, we're choosing fantasy over reality, escape over responsibility, flags on Mars over forests on Earth. Dr. E.O. Wilson, the great biologist who recently passed away, proposed something called the half-Earth concept. Dedicate half of Earth's surface to nature, allowing ecosystems to recover and biodiversity to rebound. It's achievable. It's practical. It would secure the biosphere for millions of years. And it would cost a fraction of what Mars colonization would cost. But it's not glamorous. It doesn't capture imaginations like rocket launches do. It's the hard, unglamorous work of stewardship rather than the exciting fantasy of exploration. And that's exactly why we need to do it. The astronomer Carl Sagan, who inspired millions with his vision of the cosmos, also understood this. In his book, Pale Blue Dot, he wrote, "Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Like it or not, for the moment the Earth is where we make our stand. For the moment, but also forever. Because the biological, physical, economic, and evolutionary constraints we've explored aren't temporary. They're fundamental. We're not leaving Earth because we can't. The universe has made its position clear. This is our home, our only home, our eternal home. And accepting that truth isn't pessimism. It's clarity. It's maturity. It's the beginning of wisdom. Now let me tell you why this matters more than you might realize. Why understanding that we will never leave Earth is actually the most hopeful, empowering truth humanity could discover right now. Because once we accept our cosmic address, once we truly internalize that Earth is not a stepping stone but a destination, everything changes. Right now, somewhere in the world, engineers are working on spacecraft designs for Mars. Brilliant minds solving complex problems. Imagine if those same minds were working on carbon capture technology, or fusion energy, or sustainable agriculture, or ocean cleanup systems. The intellectual capital being invested in impossible dreams could be redirecting toward achievable solutions. The shift in focus would be immediate and transformative. Think about the psychological weight that lifts when you accept limits. You stop beating yourself against walls and start working within boundaries. You become more creative, more focused, more effective. The same applies civilizationally. Once we accept that we're staying on Earth, we can stop wasting energy on escape fantasies and start focusing completely on making Earth work. The clarity of purpose would be revolutionary. Dr. Vaclav Smil, one of the world's leading energy experts, calculated that if we redirected all space exploration funding toward terrestrial sustainability for just 10 years, we could accelerate the renewable energy transition by decades. Solar, wind, storage, grid infrastructure, all could be deployed globally at scales that currently seem impossible. The return on investment would be immediate and measurable. Reduced emissions, cleaner air, healthier populations, stable climate. Compare that to the return on Mars investment. Nothing. A few people living miserably on a dead planet, contributing nothing to the other 8 billion of us. Here's what will blow your mind. Some of the biggest advocates for space exploration are starting to come around to this position. Dr. Robert Zubrin, who wrote The Case for Mars and spent decades pushing for human Mars missions, has recently softened his stance. In a 2022 interview, he admitted, "I still think Mars is fascinating, and we should study it extensively with robots. But I've come to realize that the case for human missions in the near term is weaker than I thought. The resources required could do more good addressing Earth's challenges. Even true believers are recognizing the math doesn't work. Think about what a civilization fully committed to Earth would look like. Cities designed around nature rather than against it. Energy systems completely renewable and distributed. Food production localized and regenerative. Transportation electrified and efficient. Economics measuring well-being rather than growth. Education focused on ecological literacy. Politics driven by long-term sustainability rather than short-term profit. We could build paradise on Earth, not metaphorical paradise. Actual paradise. And it would be easier than getting to Mars. The technology exists right now to house, feed, and provide clean energy to every human on Earth sustainably. The barrier isn't technological. It's allocation of resources and political will. We're choosing not to solve these problems while simultaneously claiming we'll solve much harder problems on Mars. The contradiction is absurd. If we can't feed everyone on a planet covered with fertile soil, abundant water, and breathable air, how would we feed anyone on a planet with none of those things? Here's a thought experiment. Imagine humanity in the year 2100. In one scenario, we spent the 21st century trying to colonize Mars. We poured trillions into spacecraft, habitats, and supply missions. We lost hundreds of lives to radiation, equipment failures, and psychological breakdowns. We established a small, struggling colony of a few hundred people living in constant danger. Meanwhile, Earth heated by 3 to 4 degrees Celsius. Hundreds of millions were displaced by sea level rise. Ecosystems collapsed. Mass extinction occurred. But hey, we have a flag on Mars. In the alternate scenario, we spent the 21st century healing Earth. We transitioned to renewable energy. We restored forests, wetlands, and oceans. We developed sustainable agriculture. We stabilized the climate. We ended extreme poverty. We achieved a balance between human civilization and natural ecosystems. 8 billion people living prosperously, sustainably, in harmony with the planet that created us. Which future would you choose? Which future honors the gift of existence more? Dr. Kim Stanley Robinson, who wrote the famous Mars trilogy novels about terraforming Mars, has spent recent years writing about sustainable Earth futures instead. He realized that the more realistic and detailed his Mars colonization scenarios became, the more impossible they appeared. His recent novel, The Ministry for the Future, focuses on climate solutions on Earth. In an interview, he said, "I used to think Mars was humanity's future. Now I realize Mars is a thought experiment that helps us understand Earth's value." The more seriously you take Mars colonization, the more you appreciate that Earth is a miracle we're squandering. Think about water for a moment. On Earth, water falls from the sky. For free, it flows in rivers. It fills lakes and oceans. You can walk outside and water will literally fall on your face. On Mars, water is frozen underground and would need to be mined, melted, purified, and carefully recycled, with every drop accounted for, because loss means death. Now consider that we're polluting Earth's water, treating this freely available life-giving resource as a waste dump, while fantasizing about moving to a planet where water scarcity would be total and permanent. The insanity of it should be obvious. Or consider air. On Earth, you breathe without thinking about it. Trees produce oxygen. The atmosphere is perfect for human respiration. It's free, abundant, continuous. On Mars, every breath requires energy. Oxygen must be produced through electrolysis or extracted from the atmosphere and concentrated. The moment your oxygen production stops, you die. You'd spend every moment aware of breathing, knowing it costs energy and resources, that each breath depends on fragile technology. We have an atmosphere that works perfectly, and we're filling it with carbon dioxide while dreaming of a place where we'd need to manufacture every breath. Here's what keeps me hopeful despite everything. Humans are adaptable. We are creative. We're capable of remarkable change when we face reality clearly. The same ingenuity that lets us imagine Mars colonies can be redirected toward Earth solutions. The same courage that would be required to leave Earth can instead be applied to saving it. The same resources, the same brilliance, the same determination, all of it focused where it can actually make a difference. And the work is already beginning. Renewable energy is now cheaper than fossil fuels in most places. Electric vehicles are becoming mainstream. Reforestation projects are underway globally. Carbon capture technology is improving. Sustainable agriculture is spreading. The transition has started. What's needed now is acceleration, commitment, and the abandonment of distracting fantasies that sap our collective will. Think about legacy. Every human who has ever lived, every person who has contributed to art, science, philosophy, culture, all of it happened on Earth. Shakespeare never needed Mars to write humanity's story. Einstein didn't need to leave Earth to understand the cosmos. Mozart composed on Earth. Da Vinci painted on Earth. Every moment of beauty, every act of love, every triumph of human spirit occurred within Earth's embrace. Our legacy is here. Our meaning is here. Our purpose is to honor the planet that made us possible by ensuring it thrives for billions of years to come. Dr. Robin Wall Kimmerer, a botanist and member of the Citizen Potawatomi Nation, writes about the indigenous concept of the honorable harvest, taking only what you need, using everything you take, and giving back more than you receive. Earth has given us everything. Our entire existence is a gift from the biosphere. The honorable response isn't to take everything and leave. It's to give back, to restore, to ensure that future generations receive the same gift we did. Mars offers nothing. Earth offers everything. The choice couldn't be clearer. What if I told you that the greatest adventure humanity could undertake isn't reaching another planet, but saving this one? That the most profound exploration isn't outward, but inward, understanding our place in Earth's ecosystems and learning to live as one species among millions rather than as dominators? That the real frontier is sustainability, the real challenge is harmony, and the real achievement would be creating a civilization that lasts not centuries, but millions of years, because it learned to live within planetary boundaries? This is the reframing we desperately need. Stop seeing Earth as a prison and start seeing it as a sanctuary. Stop seeing leaving as freedom and start seeing it as exile. Stop seeing Mars as opportunity and start seeing it as what it is. A dead planet that would kill you slowly while you watch the only living world in the known universe die from neglect back home. The psychological shift changes everything. So here we are at the end of this journey together. We've explored radiation that shreds DNA, gravity that owns every cell in your body, immune systems that collapse in space, bones that dissolve, muscles that atrophy, minds that break, distances that defy human endurance, energy requirements that exceed our capabilities, economics that make no sense, and evolutionary constraints that can't be overcome without ceasing to be human. Every angle of analysis reaches the same inescapable conclusion. We will never leave Earth. Not because we lack courage or vision or technology, but because we are Earth life, adapted through billions of years of evolution to thrive in one specific environment that exists nowhere else in the accessible universe. We are not cosmic explorers trapped on a planet. We are planetary organisms perfectly suited to our world, and leaving it means dying in 1,000 different ways simultaneously. And that's okay. More than okay. It's beautiful. Think about what it means to belong so completely to a place that you cannot exist elsewhere. It means Earth isn't just your home. It's your identity. Every breath you take is a gift from photosynthetic organisms. Every bite of food is energy from the sun, transformed by Earth's biosphere. Every moment of existence connects you to the intricate web of life that makes this planet unique in the observable universe. You're not on Earth. You are Earth, temporarily organized into a form that can contemplate itself. The loneliness we feel when we look at the stars, that ache to explore the cosmos, it's real and it matters. But it's not a call to action. It's a recognition of mystery, an appreciation of vastness, an acknowledgement that we are small but meaningful parts of something larger. We can explore the universe through telescopes, mathematics, physics, and imagination. We can send robotic emissaries to other worlds. We can understand cosmic evolution and our place in it. We don't need to physically go there to know it. Dr. Brian Cox, the physicist and science communicator, said something that resonates deeply. The universe is probably filled with simple life, but complex, intelligent, technological life is likely extremely rare. And if that's true, then Earth isn't just our home. It's precious beyond measure. The only place in possibly billions of light years where the universe can contemplate itself. That makes staying and protecting this world not a limitation, but a sacred responsibility. Think about your own life one more time. The people you love are on Earth. The places that move you are on Earth. The food you enjoy, the music that touches you, the books that expand your mind, the nature that brings you peace. All of it exists here and only here. Mars offers none of that. It offers struggle, suffering, and early death in service of nothing. The choice isn't difficult. Earth is everything. Mars is nothing. And yet we're still spending billions on Mars missions. We're still teaching children that humanity's destiny lies in space. We're still avoiding the hard truth that would set us free. This is it. This is our world. Our only world. Forever. And that fact should fill us not with despair, but with overwhelming gratitude and fierce determination to preserve what we have. Here's my challenge to you. The next time you see a news story about Mars exploration, ask yourself what else that money could accomplish. The next time someone talks about humanity becoming a multi-planetary species, gently offer the evidence we've explored today. The next time you feel despair about Earth's future, channel that energy into action that makes Earth better. Vote for climate-focused politicians. Reduce your carbon footprint. Support conservation organizations. Educate others. Plant trees. Change careers toward sustainability if you can. Every action matters. Every choice compounds. We are living through the most critical decades in human history. The decisions we make now about how we treat Earth will echo through millions of years. Future generations, if we ensure they exist, will either thank us for choosing wisdom over fantasy, or curse us for squandering our only chance at sustainability while chasing impossible dreams of escape. The responsibility is overwhelming, but so is the opportunity. What if humanity's greatest achievement isn't reaching Mars, but creating a civilization on Earth that lasts not thousands, but millions of years? A civilization in balance with its biosphere, powered by renewable energy, living within planetary boundaries, preserving biodiversity, allowing ecosystems to flourish. That would be a legacy worthy of our potential. That would justify the billions of years of evolution that created us. That would mean something. We will never leave Earth, not as a species, not in any meaningful numbers, not while remaining recognizably human. And that's the truth that will set us free. Free from impossible dreams, free to focus on what matters, free to build the paradise that Earth could be, free to accept that being bound to one beautiful, life-filled planet in an otherwise dead cosmos isn't the limitation. It's a gift beyond price. Look around you right now. Feel gravity holding you. Feel air filling your lungs. If you're outside, feel sunlight on your skin. If you're inside, appreciate the shelter built from Earth's materials. You are home. You have always been home. You will always be home. And home, this magnificent blue marble suspended in the cosmic dark, home meets you. Not your dreams of elsewhere, not your plans to leave, your commitment to stay, your determination to heal, your love for the only place that has ever loved you back by keeping you alive. This is why we will never leave Earth. Because we can't. Because we're part of it in ways so fundamental that separation means death. Because every law of physics, every evolutionary constraint, every biological necessity ties us to this world with bonds that technology cannot break. Because the universe itself has conspired to keep us exactly where we are. And because, if we're honest, we don't want to leave. Not really. We just want to believe we could, to avoid facing the responsibility of the gift we've been given. So let's stay. Let's commit. Let's choose Earth over emptiness, life over death, reality over fantasy. Let's build the future here, the only place it can exist. Let's honor our home by becoming worthy of it. Let's prove that a species capable of imagining the stars can be wise enough to cherish the world that made those imaginings possible. We will never leave Earth, and that's the most important truth humanity can learn before it's too late. Thank you for taking this journey with me. Thank you for facing hard truths. Thank you for being here, on Earth, where you belong. Now go make it better. Go make it worthy of the miracle it is. Because you can. Because you must. Because there is nothing else. No plan B, no escape, no other home. Only this, only here, only us, only now. And that's enough. It's always been enough. It will always be enough. Earth is enough. We just need to recognize it, protect it, and dedicate ourselves completely to the only future that actually exists, the one we build together, here on the pale blue dot that is everything.